Gotcha.
Okay, so writing storage engines. Okay, I'm actually impressed this many people showed up. In fact, I had suspicions there might be like 8 of us, and I knew we would know half of the people by name. Or at least most of it would be MySQL employees, which I don't actually see that many MySQL employees, which is bad for MySQL employees because they actually usually need to learn this stuff too. My name is Brian Aker. I'm the Director of Technology, Architecture, something like that, for MySQL. Today, what I'm going to be talking about is the storage engine API. Just to warn you, I'm going to be breaking rules in this talk, which is called, you're never supposed to actually show source code in this talk, in any type of presentation. Well, I can tell you there are 60 slides of source code, so I'll be breaking that rule pretty dramatically. Just for, if you can follow C code, you'll probably be okay. If you can't follow C code, then hopefully me talking about source code is entertaining. Because if not, you probably won't be that excited about it. So, a couple of thoughts, especially since we now have the 2 people who needed to run for the door since I mentioned source code. What we're going to talk about, a couple of thoughts on this. Going into this, something you should consider. Start from an example engine. Don't just open up your editor and try to start from scratch. That's a really bad idea. This is a pretty complicated API. I think it's fairly easy to understand once you get into it, but don't just try to open up an editor and start writing from scratch. It's probably not a good idea. For next thing, I'm only talking about 5.1, so I'm not talking about how to integrate engines in previous versions, because it was painful. But what I want to suggest you do is make your engine pluggable from day 1. Don't try to integrate it into the code. That's a great way to get something that nobody will actually ever be able to use. And pluggable engines are nice because you don't have to recompile the entire server when you're working on them. You load it, you test it, you core the server, you figure out you did something wrong, you put another one in, and you start going again. Don't try to just do a straight server integration from the get-go without making it loadable. It's just a really bad idea. Third thing, automate your testing. Automating testing is key to actually keeping the storage engine running. It allows to know that your testing will work each and every time. There's a system called MySQL test, which makes it relatively easy to integrate and automate tests. I will warn you though with it is that it wasn't really designed for loadable engines, so you got to do a little bit of kind of juggling to actually make it work, which is a shame. On the other note though, we have actually the other testing system, which is Slack, works just perfectly with loadable engines today, so it works just fine. You can install it and start it running. The last part in here is when in doubt, see how another engine actually works. This is open source. There's no harm, no foul in looking how other engines actually integrate with this service layer. And that is something to know that looking at other engines and seeing how they're written is really going to make a lot more sense to you. I'm going to be showing you a number of engines, and throughout my slides, I've made a point of showing off different engine source code and how they do it. So I think there's probably more than a dozen engines when I walk through the API I use just to show you how different people do it. And I'm going to try to talk about best practices in doing it because there are best practices when integrating a storage engine and there are poor practices. And the poor practices sometimes you need to do because, well, you just got to do them. But if you can stick to best practices, you're going to find that long term, things are much more easier to maintain. So, on with the show. Oh, that's great. First thing, the server. It's written in C, C++, somewhat similar. Mostly the server looks like C. It really doesn't look like C++. It's, in fact, the joke usually is it's C++. It is not the best shining example of C++ code to exist. In fact, I can show you places in it which show that it is some of the worst concepts ever in C++. The good thing is the engine interface is mostly cleaned up. If you want to talk to Bar later about fields, we can talk about bad C++. But for the most part, think in mind that the server is C. A lot of the storage engines we implement are C. A growing number of the storage engines that we talk about nowadays are C++ though. So the balance and tide of C versus C++. So either work or just fine. Majority of the code is actually written in C. The parse tree and the optimizer were implemented in C++. The handlers were implemented in C++. And really the only time you ever deal with any kind of functionality which is written in similar to the server is the compare operators, the compare and operation swap stuff in MySQL and in the strings library. The server's process model is this. It is multi-threaded, so it's not a process-based system at all. It actually uses p-threads. It uses p-threads from the beginning. You can either say that's forward-looking or laziness, depending on your belief. The fact that it actually uses threads in this model. We are starting to tinker with breaking the one process to one connection, though, so thankfully nobody really relies on that in the storage engine environment, but we are starting to break that a little bit. There's a very minimum overhead in clients. We keep a very small stack. MySQL was originally written to work in memory-tight environments. It was from pretty much near the early stages, always 64-bit, so thankfully it's pretty 64-bit determined. And it's really designed to be in multiprocessor environments. In fact, the general limitations that exist of MySQL in an SMP environment is not the MySQL source code itself, but it's actually the engines themselves. The engines are the ones that tend to limit, they limit 64-bit, but they limit multiprocessing environments. If the engine really can't work very well in multiprocessing environments, it shows up. MySQL is very rarely the actual limiting factor in SMP operations. It's almost entirely the engines. Basic architecture to get into this. MySQL has a parser, an optimizer, and a retrieve store environment. I also usually refer to that as the shim layer, which is the layer that allows us to connect to multiple engines. So that connection component that actually is written for each engine. Many of them are copied out of each other. In fact, I find it hysterical sometimes. I'll see a new engine in the market and I'll go, oh, I remember writing that 3 years ago. I don't know where they copied and pasted that. So a lot of the shim layers are very, very similar. And I think I'm probably one of the few people who go through and tend to, if we figure out something that looks better, go back and retroactively fix it through all the other engines. So the engines are a little bit, the more modern an engine has been implemented, probably the more modern both its comments are, and modernize the actual interface it is itself. And this just shows a number of the engines that actually exist. The thing to keep in mind, and also MySQL compared to academic projects that tried this in the past, MySQL is fully relational and fully between multiple storage engines, which is a little bit different than what we've seen. There are a number of early databases that would try to do multiple storage engines, but they wouldn't be relational between them. MySQL breaks that by the fact that you can do a select and do a join against a solid table, an entity table, and a Falcon table, and it all just works. And this is the fact that its optimizer internally is a cost-based federated optimizer. Every time we add a new kind of storage engine, we add a new, we tend to extend out what we can actually do internally so we can handle more types of more environments. When we added cluster, we added more. When we added archive, we added more. When we added federated, we continue to extend it out. So the more storage engines we get around to learning about, the more that we tend to extend the interface and refine the interface. So between each version, the interface gets refined just a little bit every time. I think the most recent addition was in 5.1. We actually fixed the key system so that if you wanted to, you can now have bitmapped indexes, which is something that was never supportable internally before, but now you can actually do a bitmapped index. And like I said, there are a lot of engines sitting up here. Some MySQL owned, some other people owned. I've written a few of these, and there are a number of people, a number of organizations that have written others. So the first thing, the first slide that's actually got some code in it, is I want to talk about the plugin structure itself. MySQL has to have a way of loading an engine when it starts up. So that's called the plugin system inside MySQL. And for every plugin, there's a declaration that looks like the slide that's just the slide you're seeing right now. And that's the declaration for an actual plugin. Now, this can be a daemon plugin, it can be a full text plugin, it can be a UDF plugin. But in this case, what we're going to talk about in this talk specifically is a storage engine plugin. So this is what a storage engine plugin looks like. The first piece is going to be the declaration of what it exists. In this case, okay, it's a storage engine. The second part of it is going to be a reference to a structure. That structure is used, or the design of it is to be used for being able to extend information in the future. Today it only actually for storage engine has one value in it, which is the version of the storage engine interface that the engine actually implements. So at this point they're pretty much a copy and paste of every other engine that exists today. The next part in there is the actual declaration of the name of the engine. So in this case, what you're looking at is the memcache engine. The next part is who implemented it. The next part is the license. Sorry, the next part is the description string. When somebody does show plugins, that's what they're going to see. The component after that is the license. Today we don't do strict checking. We don't kernel tainting inside of MySQL. We will do it at some point in the future. Namely, if you were to load a module into a GPL server, which was not GPL, we'll flag that as a warning to the user and say, what you've just done there is a violation of the GPL. We don't do that today, so today they would happily load up, but in the future we'll actually add that. So currently today, I think the only thing we list is GPL, BSD, and proprietary. If you need another license type that we don't implement today, best thing to do is probably write email to the internals@mysql.com mailing list, and we can add another license type. It's just when I was writing this up in the middle of the night, I had 3 licenses, and so I put them in there. Yeah, the main list, by the way, if you walk out of here and you've got questions, the main mailing list for doing storage engine work is internals@mysql.com. It is not the place to ask, does my schema look good? Or should I use a key here? It is a mailing list which is devoted entirely to the source code of the server. So if you read it, you'll see patches, you'll see internal changes. It's a very technical mailing list. It's also very, I doubt there's more than 2 or 3 pieces of email on it a day, unless we have an argument. And then generally that doesn't even go beyond 4 or 5. We save the good arguments for the internal, for the mailing list of employees only. So the internals list is pretty good. The next piece in here is the init function. This is what gets the show running. If you start up the database, the init function is called to start up the storage engine. If you shut down the database, the next function, which is the what do I call it in there? The done function. We have different ways. We sometimes call things done, finalize, or dinit. All the same thing, sir. We just seem to use the terminology 3 different ways. I didn't use the word done. That's not me. I think I'm dinit. So the dinit function, or the done function, is called whenever the server is shut down. So if you need to do any kind of global initialization, when you start up your engine, the init function is where it's got to happen. If you're going to shut down stuff in your engine, that happens in the dinit. Something also to note, when a plugin is loaded, the plugin also gets a init called. When the plugin is deloaded, the dinit is called. If you want to make a perfect engine, what I think we'll see happen within 5.1 is people will want to upgrade engines and not upgrade the server. So they're going to end up with a 5.1.46 version server and say it's just fine, but I see that there's a bug fix in your engine and I'm going to upgrade it. So the point of this is that you can do an online upgrade of actual engines, which means you need to think about global variables. If you implement global variables, you're going to hose yourself from being able to do that. So just something to think about. Don't use global variables. You wouldn't think I need to say that, but I do. The other thing that you see next is the version of your engine. So if somebody does show plugins and they look at the version number, that's what's going to appear there. The next 3, 1 is implemented and 2, the tree is available. The next one is the status variables. Status variables are variables that have callbacks. So for instance, if somebody does a status variable foo, we make a callback to the engine to actually ask you what about foo. And the interface there implements the status variables. Also, status variables can be updated, so you can be told when somebody updates the status variables. Therefore, you can abuse the hell out of them. So people have implemented them to do like temporary tables and tell engines and start backup and all kinds of stuff. So if you're looking for an abusable interface, welcome to your first abusable interface. And that's actually how the status variables work. The second set of ones is the system variables, which is show variables, and the other is the config option, which is MySQL. Those are not currently in the current 5.1 tree, but will soon be put in it. There's a work log tree at mysql.bkbits.net where you can see the work log tree for that, and you can see how they're implemented, but you might want to just wait a couple of weeks and it'll be finally in the server for real. It's the last key component that hasn't been done yet that will really It allows, for instance, to take NODB and make NODB pluggable once those two pieces are done. We believe. Now, what I'm going to show you is a simple handlerton. When we talk about the instance of a storage engine, we call that the handlerton. There is one handlerton per storage engine, but there are many handlers. And handlers, you might as well consider them conceptually cursors. So whenever I say handler, you can think of it as a cursor, and a handlerton really is the storage engine. This is the init function from the example engine. If you look in the skeleton engine or you look in the example directory inside of MySQL, this is what you'd actually find. You can see a couple of things that it does. One, the void pointer P is going to be a structure that you're going to fill out. That handlerton structure you fill out is what's going to determine the behavior of your storage engine. Not a particular cursor call, but the behavior of the storage engine itself. The next thing that you'll actually see is any code that needs to be done for startup. In the case of, for instance, the example engine, in fact, most of the engines tend to keep some kind of shareable memory available around to do resource working from. There's also some engines that start up their own threads. That is where you see this kind of code implemented. So if you need to start up some kind of a cleaner thread or some kind of a flush thread, this is the place where you implement those pieces. If you need some kind of shareable components to keep track of lock information, this is where you do it. In fact, what you're seeing there is the hash init, which is the lock structure for the example engine. There's an example locking structure that are exactly in the example engine. The other thing you'll see is the state. You can return to this state if you have an internal problem. You can set a state and say, you know what, startup didn't occur. You can set that. You can set up you set up the pointer to the create handler method. The create handler method, or sorry, function, is going to be used to create handlers. Handlers are in C++, so they're going to be objects that are going to be called. That callback function that we have there, the example create handler, is going to be the callback function to create the object. For the most part, you can copy and paste that out of another storage engine. Not seen anybody ever do anything unique with them so far. And flags are showing which flags that start describing how the storage engine itself is going to work. Here's a little more of a complex one. DB type is a historical. You don't need to worry about it if you're in this room. It used to be that we had to keep a number around to keep track of engines. Nowadays we use it by strings. The whole number thing wasn't really very expandable. Only legacy engines have them. So Federated has one, but your engine would never have one. The next thing you see there is federated commit. Commits obviously are something which are storage engine wide. We have to be able to communicate across many tables, many cursors. So that's a storage engine wide comment. So if you have a commit operation, this is where you would load it into the handlerton structure. So the handlerton structure would get the commit statement. Many, many slides later, I've got an example of how a commit actually works. So I'm going to talk a little bit about transactions today. The other one you see is HT alter not supported. That is a flag describing an engine's behavior. These continue to extend as we add new behaviors. And what this means is that federated doesn't allow an alter table. You have to either create federated tables or drop federated tables. You can't actually alter them. And if you think about it, that makes sense because, well, you'd be trying to alter something on a remote server, which is not exactly a good idea. So this is one flag showing off one behavior. And there are many flags that actually show other pieces. I've got some slides later on to talk about that. Now, the handler is the key to most everything. The handler is the cursor. The handler itself is what we do reads and writes from, is what we do inserts against, is what we do updates against, we do deletes. And I just realized I haven't been asking if anybody has any questions. So let me stop here for a second. Has anybody had any questions so far? Shoot.
The previous slide, the little function, what is it?
Bingo. Yeah. What he asked was, is everything in lowercase, are those all callback functions? And the answer is yes. And is everything that's in uppercase just flags? And the answer is yes, they're just flags.
Is there a reference for like the flag?
Very poorly. The answer is that there is, it's documented in handler.h. But I can tell you that some of them are not exactly strict as to what they do. In fact, let me put it this way. Some of them I have to look at every time because it makes no sense. Which I would love to say it's better. There's also documentation inside of ha_partition.cc. Michael documented quite a bit in there. This is a very use the source loop kind of situation when it comes to these. This needs to be fixed. One good news, by the way, is I think I got confirmation that we finally, I don't know, do I term you beat up? Anyway, we got the documentation guys to use a term called a wiki. So the internals documentation, which was in Texi, which was impossible, which then got moved into Doxygen, no, so not Doxygen, but in DocBook, which was also impossible to edit, will soon be going into a wiki. I think the term was not in over our dead bodies, so I think there was somebody who died in this, that's my understanding. So all of that's now going to go into a wiki. So once this goes into wiki, I think we'll see updates much, much more quickly, because I can tell you what, while I have no interest in updating Texi, if I have to look up one more time at least what one of the Hamilton means, it would just be much easier for me just to go and document in the wiki so I can stop looking it up. And I know there's at least a couple more people in the room who feel the same. I see Brian over here shaking his head. Yeah, he's pretty, either that or calling me and asking me questions. So anyway.
So I had a question.
Yeah.
You mentioned about the GPL tape.
The which?
The tainting,
Yeah.
tainting issue. So you ship some non-GPL storage databases, right?
MySQL doesn't, and there are non-GPL engines that exist out there. But MySQL stuff doesn't have any engines which are not GPL. But I know that people are going to write them. I mean, it just seems obvious to me that people will write them. Yeah, but that's actually open source. No, that's actually why I added the BSD flag. I was saying there.
It's neither is it BSD.
I don't know what to call it. Yeah, it's a good thing I removed it from the code. But this is the problem that has come up, which is that we're going to have to put in a number of these. And at the end, you know, if you need to explain your license so much that it's not one of the common licenses, then maybe you should mark it proprietary and force the user to actually figure out whether it violates the GPL or not. We're trying to be very simple in the approach. That's part of the reason why I did both GPL and BSD. BSD doesn't violate the GPL. GPL doesn't violate the GPL. I should probably put an LGPL one in. And right now, everything else is proprietary, so you need to figure it out for yourself if it violates the GPL.
What do you mean when you say it violates the GPL?
Violates the GPL means if you're adding proprietary code, if somebody has shipped a component, which is a proprietary component that then links into a GPL server, it is arguable that if that component itself is only usable in this framework, then it probably falls under the domain of the person who's supposed to ship source code to it as well. And I really don't want to have a long lecture on GPL versus non-GPL, because there's not a bar. It's just gets complicated. So that's part of also the reason why today there's GPL, BSD, proprietary. So, but I do actually expect that people will push and publish storage engines where they won't release the source code to them. So that's just, you know, part of the world is that, you know, that kind of stuff happens, and, you know, that's the way some people believe and some people don't believe it. I as an engineer, not entirely my problem. I say that hoping that. Any more questions? No, I don't. But during the break, I can give you a copy of it on a disk, and maybe I might be able to get it up on a website by the end of the tutorial during the break. Any other questions? Okay. The handler. The handler itself is a cursor. It is, like I said, implemented in C++. You will have your handler will inherit from the main handler class. The handler class has many default methods in it, so it's not that you have to implement every method. There are required methods, and I'll talk about this, which ones are required. It has today both table-level operations and cursor operations. We are trying to move out the table-level operations because they really don't belong in a cursor. But in the beginning, all there was the handler, and as we move forward, we redefine the interface. This interface is redefined between versions, so you know, if you implement 5.1 to go to 5.2, it's the same right now. 5.2 to 5.3, there'll probably be slight changes in the interface. We're trying to make this, you know, fairly stable, but it's still fairly internal-ish. This is a database kind of interface, so we will be making changes. So, there's actually a lot more to the handler than I can even cover in 3 hours, but we're going to take a shot at a large chunk of it. But just to know, this is a very long thing to learn everything about how storage engines are written. So probably the thing one of the things that was asked for is how do you actually define features? You can define features by using three pieces. You can do them by table flags, index flags, and Hamilton flags. Table flags are used to say what is going to be implemented into the table. Some of the table flags should probably be, I'm going to critique the interface by the way we go through it. So the table flags, some of the table flags probably you would say need to be in Hamilton flags, and we'll probably merge the two concepts at some point. But today they're still separated. The Hamilton flags, these are some examples. Hamilton, close cursor at commit. If a storage engine has implemented cursors, does it know how to actually close its own cursors at commit, or do we need to close the cursors at commit? InterDB, for instance, needs to have its cursors actually closed for it. Hamilton, alter table not supported. The alter table isn't supported, meaning that there is no way to actually alter these tables at all. Federated is an example. You don't want federated trying to change tables on remote connect on remote servers. So that's an example of one. HT hidden. HT hidden means that if someone did a show engines command, it won't actually show up as an engine that exists in the server. So the existence of the engine can actually be hidden. The next one is hdone not user selectable. Means you can show that certain engines exist, but the engine can't actually be selected by a user. For instance, partition is an example of an engine that exists, the partitioning engine, but you can't actually create an actual table in the partition engine itself. So just to give you an example of what these different pieces are. Hamilton no partition, that means that this engine, storage engine, can't handle partitioning at all. So that's another kind of flag. In theory, all engines can support partitioning, so this one's a little on the strange side, but actually come to think of it, no, there's two they can. Table flags, like I said, some of these are probably more belonging to the storage engine layer, but today they're implemented on the table. Two flag systems need to be combined. Table flags, no transactions. That means my storage engine doesn't implement transactions, so I need to declare this because we can't handle transactions if you start trying to call commit against me. Table scan on index. What that means is that's a key to actually telling the optimizer. This storage engine, when it's actually doing a scan, so it's looking at all rows, it's going to be using an index. The optimizer can make use of that information, so that's something to know about it. HA can index blobs. Can the storage engine actually index blobs? Blobs, my ISIM can't, Heap can't, but there are storage engines that can actually index full blobs, so it's implemented. So this shows you about functionality. Can full text. Does the storage have full text indexes? There's another one for R-tree indexes, so if you have R-tree indexes. Bitmap indexes are implemented such that you don't actually have to declare a flag, but for at least the other two, if you want to do full text indexes, you need to declare it. Is the storage engine file-based? Is the storage engine really a set of files on disk? Because if it is, that means that things like drop table can be implemented easily by just sending a simple command of, we're going to shut you down, and then knows that it can just unlink the files directly in the disk in the directory itself. So just in cleanup commands, is it a file-based storage engine in the first place? And file-based really is file-based meaning tables or individual files instead of a block-based one like MDB, which is large block section or Falcon or any of the others. Is there any question on table flags? There's about 27 of these, as far as saying feature-wise, so there's an awful lot of pieces up here to know. Like I said, R-trees, yes?
This first of all, engine file-based, like so how does that?
Yeah, it's still not file-based though, because it has to keep log information going, and it has its own data dictionary. Yeah. Yeah, really this is just a flag saying this storage engine can be managed a little bit like files. So, and some of the advanced engines can actually be manipulated by files. Not that it's really all that publicly available nowadays, but like for instance, the Gemini engine can actually do file-based. So, and how many people in here even know what the Gemini engine is? Hey, some history. It was one of the early transactional engines. I still have it compiled on 5.1. Someday I'll publish it. This is actually implemented inside of the handler.h. So if you look at the example in handler.h, you'll see a callback to a thing called table flags. You fill it in that callback called table flags. Any other questions about this? Next piece is index flags. Index flags say what kind of indexes you actually implement. Do you implement B trees? Do you implement hash indexes? Things like, can you read forward in your indexes? Can you read previously? Some B tree implementations allow so that the B tree can be scanned in a backward state. Some allow for a forward state. Some are whole indexes, meaning a hash index. This basically kind of gives us the behavior of your actual index system, tells how we can call your indexes, and when your indexes are going to be usable enough inside the optimizer. Any questions about this? There's only about 9 of these. Yes?
What are the
For the which? HA read order? That means is the engine, if you read on an index, will the rows be retrieved in the order of the actual index? So if you have an ordered B-tree index, are you going to send us rows back that are already ordered, or are you just going to be giving us arbitrary trees back? For instance, you take a network engine such as like NDB, it's got B-tree indexes, so it has an ordered read, but it sits there and goes across the network and fetches many different types of rows all at once. So the row results that come back will not automatically be ordered correctly. Where in the case of MyISAM always returns records in the order of the actual index. Falcon, for instance, to give an example of another type of engine, Falcon's index works this way. Falcon looks at its index and then builds a bitmap of what rows it needs to retrieve. It then retrieves rows in the physical order of the disk, the physical order of the rows on disk. So its rows, while it originally had an index, are not automatically pre-ordered. Most of the storage engines in MySQL up until 4.1 all had ordered indexes. So this was something that we had to add once we had clusters. This cluster doesn't have ordered indexes, or it doesn't automatically order the results that's coming back. Yes?
Is there not about the storage engine support the EBCs or other features? I mean, is user runtime or user compile?
I'm sorry, what?
The features, the different features like the kind of indices supported by the storage.
Yeah.
Are you taking advantage of that at runtime in the SQL Server community or at compile?
The answer on that is he's asked, can you adjust features, are all features locked to compile time, or they can be adjusted at runtime? You just hit on the fundamental difference between Handlerton flags and table flags. The Handlerton flags are compiled flags, but anything that's called in table can be adjusted. Same thing with index. So for instance, if an index flag is called on a particular index, you could actually return and say, well, my primary index is always ordered, but my secondary indexes are not always ordered. So based on an index flag call, you can actually adjust that. I've got a slide here, I'll show you how to do that. These, if you wanted to see an example of that, heap.cc, that's the memory engine, shows an example of how it can switch between B trees and hash indexes. By the way, is this room hot for people? Okay, turn the lights even hotter. But yeah, I wonder if we can, is there anybody in the back from the, nope. Yeah. Let's see if we get them to just turn down the air, sorry. Okay, it's working really well. Correct. Yeah. You don't have to hard code table flags, because they're actually called in a function and a callback. Any other questions? Yes. Yes, they're established during plug-in time. This is just the thing to know about the flags. The flags, I'm trying to get people to start publishing on internals when they add new flags for new features. That's not happening just yet, so I personally go and just read handler.h every so often and see if anybody's added something. Kind of bad that you have to do it, but that's kind of the way the system works right now. Now what I want to do is I want to get into actual table object methods, which talk a little bit more about the pieces that put together tables and take apart tables. So the table level object methods are the pieces that frankly probably belong in the Hamilton and probably less than the handler, but they're there today. The base extension is one call. We also have create, delete table, rename table, and optimize, repair, etc. Base extension is really easy. If you have a storage engine which is file-based, like MyISOM is, and what you see the code up there is the MyISOM one, you can declare what your file extensions are ahead of time. And so a delete table operation can actually be performed instead by the upper end and not by you, so you don't have to worry about deleting the files. It will delete the files for you. You can say this is kind of lends the argument to MySQL as a big old interface to the file system. Probably is true. In this case, but if you looked at InnoDB, it declares nothing whatsoever. So it's really up to you whether or not to use base extension. But if you use base extension, you can use the default rename table, delete table to actually do operations. And the MySQL server itself will handle the renaming of your files on disk or the deletion of your files on disk for you. This shows just the basic call, and this is also, by the way, an example of how the tables or how the table flags are called as well. You generally declare some kind of a free environment, or just statically declare them whenever you want to. But we generally tend to use callbacks to actually get that information. Create table is the heart of what actually starts up and makes everything go. For create table, we take a blank handler. So what we'll do is we'll ask for create a new object on the storage engine. So we'll create a new one of your handlers. Then we'll call the create method against it. So there is no state that exists. There is no state that exists before create table, and it's expected that no state exists after create table. That's important to keep in mind. So you can't guarantee that once create table has been called on a handler, an open table will ever be called against it, or a closed table. So everything you do needs to be the state of the actual moment of the create table. Now, what's passed into create table are three components. The first thing is the name. Now, that name is going to be adjusted based on whether or not you said you were a file-based storage engine. If you are a file-based storage engine, you will get an encapsulated name so that you can use it in a file system. If not, you'll actually get a raw name. Something to keep in mind. Identifiers are non-transferable. That means we give you an identifier to use, but we will also request the information later on based on that identifier. We don't guarantee anymore that at any point that's the identifier that the user actually used. Namely, if in the from clause they did, A as B, they may have used B. We're still going to call you by the exact same identifier. So you don't have to worry about aliases to your table name. But it doesn't also mean that this is exactly guaranteed to be exactly the name that they used in the from clause. So this is just a key we use. So something to keep in mind, it's just a key that we use. Don't assume that it's related to the actual user. Yeah?
Will you also, I think I will ask, will you also make there the schema and the catalog and things like that?
The which?
The schema on the cataloging?
Yeah. Yeah. Now let's go on to the next part. Let me answer the next piece of that. Table args is the next piece. So if you're looking at a create table, and you start seeing varchar, int, and all that, all of those components are the parts of the table argument themselves. So the table argument has all the field information. So if you needed, say you were in InnoDB and you have an internal schema, this is where you would actually extract that information and send it into your internal schema to be created. For instance, in InnoDB's internals, it creates a stored procedure around what it tears apart in the table args, and then executes that stored procedure internally in its own database. So some storage engines are very advanced internally. Some other engines, not so advanced in this case. The second part in there is the create info. The create info is the information that is declared after the end of the create table. So you say create table, field information goes to the table arguments, engine equals, comment equals, connect string equals, all of that data, row format, row offsets, all that information is stored in the create info. Now the thing to know about create info is not guaranteed, all that information is not guaranteed to be stored by the actual database. Some of it is and some of it's not. So some of that field information, if you end up using create info, you're going to have to keep it around for yourself. And there's a callback to add it if somebody ever does show create table. But that is all hints to the storage engine. It's also not required for storage engines to actually implement everything that is in the create info. Storage engines are required to implement everything that's in table args, because we're going to expect that you now know how to handle the field information that is passed in. but it is not expected that all the create information you necessarily can handle. Because for instance, if somebody did a create table and they did a connect string on MyISIM, well, MyISIM doesn't have to be a connect string. That's Federated or AWS or any of the other engines. So just to think about that, that information is not necessarily required for a storage engine to implement. Now, what you're looking here, by the way, is the the Federated engine, which is fairly simple in what it does. What it does is it creates what's called a share. The share is a concept that I think I'm responsible for. So what do you think? Which is how most of I think I implemented this in one of the first storage engines, and we've just copied it to about every other storage engine that exists today, probably has one. And it's just a structure I defined and I called share that we use to keep track of global information about the state of the current the state of the current table. I think all engines except for Blackhole doesn't have a share. And I think every other engine today out there uses the concept of the share. And I think somebody once told me that somebody's refined it and I was going to send me a patch, but I've never seen it. Yeah, you're trying to out the guy who did it. Yeah. So the thing is that you can copy that out of an example. An example shows how a very simple share works, and you may want to. In the case of Federated, you can see also where Federated does a parse URL. So it actually determines whether or not the foreign table actually exists or not. It says it just validates during the create table that it can eventually talk to the remote table. So any kind of validation upon create is done here. There's only one case where a create table is not called on the generation of the table, and that's later on. I'll talk about that. It's called discovery table. Something else you're going to start noticing in the code, you're going to notice the debug enter and the debug return. We have a full trace implementation inside of MySQL, so if you're running a -debug mode or you compile with debug, you can actually use the trace generation. The trace stuff is really cool and is really useful. I'm a big believer in what's called the APR, which is the Apache Runtime Library. We have a thing called MySys internally. The only reason I like MySys more than APR is the existence of the trace file system, because the trace file system makes developing code really easy. Because by using the server in -debug, it prints out everything to a trace file, plus thread context, plus memory context of everything that's running in the server. So you can run the server pretty hot and heavy, and then grep out anything that you need and see how it works. Being somebody who doesn't always like stepping through a debugger, I find this really, really useful. And it certainly saves from the old adage of, I added a printf statement here. These are compiled out of the server when the server is put in generally in production mode. So if it's not, the server isn't compiled with --debug, these are just compiled out as macros. But you'll see a debug enter and you'll see a debug return. And you'll see how it's done in the create statement. Delete table. Not everybody actually has a delete table. What the delete table does is it's going to be called with a table name. And that table name is that same identifier that we used earlier during the create statement. A delete table does not actually assume that a table is currently open. In fact, it assumes the table is closed. So it assumes that the table has been closed down. So by the time the delete table occurs, it assumes that if you malloc in memory, if you created anything for this engine, it's all gone. This is only for if you need to do some kind of cleanup of your own internal data dictionary, or you need to clean up some files on disk. And if you've implemented base extensions for your file extensions, MySQL will just clean them up directly and you never have to actually implement the delete table. So delete table is only required if you actually require it as an implementation. Is there, I didn't finish with the create table. Does anybody have any questions on create table? Yes.
Is there actually something in place to hand over some table parameters to a storage engine, such as the connection string, but in a more general way? Or
unfortunately,
we have to change the server every time when we need something for a new storage engine?
Today, the ways of doing this is to generally overload one of the operations that are already there. Anthony Curtis has got a patch. In fact, he should be floating around. He's a nice British guy. To add to 5.1, the ability to add arbitrary keys based on engines that can declare keys. So an engine could say, I need these 5 additional extensions added to the parse grammar for a create table, and then just apply it to the engine. He hasn't pushed that code. I don't know what the state of that code is. The other thing to know about that is, but today the answer to your question is, most people override the already used components. Like they override the comment field, they override the connection stream, they override row format. So there's a number of ones that you can kind of repurpose to your own environment if you need to.
It's actually just very nice currently.
Oh, it's very nice to repurpose them?
No, it's not very nice actually.
Yeah, I was going to say, I disagree with you. It's a hack. It is definitely a hack to override those pieces. And hopefully Anthony will get this one piece done. Any other questions about create table? Okay. How about delete table? Anybody got a question on that? I can tell you one question nobody's asked yet. How do I actually find out where my file was in the first place if it's been created in the data in the tree? There's a function called fn format. So you pass in the table to fn format, you pass in a buffer, and it will then generate the entire path to the data directory. So, you know, user local var, schema name, and then it puts in the table name. So it's called fn underscore format. Yeah. So that's how you generate a full path to finding out where you're at. And this is, for instance, the delete table to the MyISO. Rename table, pretty simple here. We give you one identifier, and we get the identifier you got to go to, and then you figure it out. I believe inside of InnoDB, for instance, they generate a stored procedure for doing this, and then just update the internal data dictionary. The thing to know about rename table is when rename table is called, there are no open instances to the actual table. So you don't have to be worried during a rename table that somebody might be reading from it. You're guaranteed that everybody is out of the table at that point. So during a rename table, that's not an issue. Any questions on this? The parameters are literally one identifier to another identifier. I didn't talk about it, but there's also a number of other table operations. There's optimize table, there's repair table, optimize table, so if you need to implement any kind of, you have a file structure such that it can be re-optimized every so often, then you can actually call optimize table on it. If you've got repair table, if you want to be able to create ability so that if somebody selects a data table and the table is currently damaged or somewhere not available, you can return value and then you can basically use keys to repair table. Repair table has three pieces that are passed into repair table. It says the level of repair table, should it regenerate, how much should it regenerate. I don't have an example up here, but just to know that if you need this kind of a level operation of repair table, optimize table, check table, it's all implemented actually in the server. And when any of these operations are in motion, any of the table level operations, I go back to the point of saying, table level operations, you don't have to be concerned that any user is actually reading from the table during any of these points. So all these operations are atomic in nature, and you don't have to be concerned about users reading or inserting. Until these finish, somebody can't insert it to a table or read it from a table. Now, let's talk about an actual insert and how an insert works. An insert works based on what's called a write row call. And what you see right here is a trace. So remember earlier when I talked about debug enter and debug return? This is an example of what a trace actually looks like. Trace is at 3, which means that it's the third thread that's currently open right now. So if you're in GDB and you're tailing this thing, you can run in GDB and use the trace file at the same time. So you can actually do operations. The level of bar shows the level of calls from the initial call of the original SQL call. So you know how many function level deep you are at any given point. And this shows an insert where the table wasn't open. So in this environment, the table wasn't actually open when this was initially called. Nobody had done anything. So the first thing Archive had to do is say, well, I've got to open up the table. So what it does is it looks, sees that the table hasn't been open, and then updates its own memory resident scoreboard on operations of tables. The next thing it does is it actually does a concept called getting a share. And when it calls get share, that's where it's implemented that shared object component. So the shared component is, like I said earlier in other examples, where it tracks its scoreboard information, its access to tables. You won't necessarily have one of these. Create record buffer is where it creates its record buffer it's going to use eventually. And then the open call finishes. So you can see how it indents and goes into actual function calls. For an insert to occur, the first thing that calls is a start bulk insertion. The next thing that's called is the actual write row itself. Now, the start bulk insertion has really three values that you're going to care about. Is it 0? If the start bulk insertion starts up at 0, that means the storage engine has no idea, or the upper layer has no idea how many rows are actually going to be inserted at this point. It says, don't know. Probably not 1, but don't really know. If it's 1, you know that only 1 insertion is going to occur. If it's a bulk insertion, the number is going to be some number greater than the value of 1. If your engine can handle bulk insertion updates, this is where you're going to actually want to optimize for it. For in the case of Archive, for instance, it uses flush boundaries. So when the beginning part of the insertion occurs with the write row, it says, this is a large bulk insertion. I'm not going to update the flush points until I complete this operation. So it actually sets up its own parameters internally to know that, hey, I don't actually need to do anything for a while. This is not going to matter. The next thing that's going to be called is the write row. And the write row is where the writing actually occurs. And the next slide is going to talk about that. The end bulk insert station means that the end of the write hasn't happened. So whenever you see that, you know the event horizon for the insertions has finished. You don't have to implement start bulk insertion or, for that matter, end bulk insertion. You can implement just write row. InnoDB, for instance, has no ability to do a bulk insertion, so it doesn't implement it. Archive does. A few other engines do as well. Start bulk is also important to know that they don't necessarily cause locks. If you're wondering, hey, if I start doing a bulk insertion, does that cause a lock in the storage engine? The answer is no. That's actually handled in another layer. So that's really an off environment. All you need to think about is, I'm about to receive rows. How am I going to be inserting these rows? And that's pretty much it. And if you walk through it, you can see the rest of how Archive works through its pack row system, where it sits there and massages the data before it gets sent into the compression buffer. Is my laptop fucked up? Oops. Is there any questions so far on this slide? Well, it's pretty simple. Well, we're starting to kind of chill now because I'll turn the air conditioning on. So. Here's an actual write row itself. This is Tina. Tina is the CSV engine inside of MySQL. Text is now anywhere. Really, that's what it means. I didn't name it after a girlfriend. In this case right here, Tina write row is called. You see something called share crash. Tina keeps track in its global buffer whether or not the table is crashed at any point. So if a crash occurs, it makes sure that nobody else looking at information is going to try to go read into a bad table. And just to mention that, that's actually, when I look at that right there, I realize something looking at that piece of code. That's not thread safe. Huh. That's good to know. The debug return how error crashed on usage. That'll cause MySQL not to continue to try to do selects against that. HA statistic increment. We have basic statistics we keep in the server basically on a per thread basis, how much insertions occurred in that thread. If you want to be able to add those values and calculate those values, you implement them directly inside of your writes, updates, deletions. There's probably a good chance we're going to remove that and do that in the upper layer here at some point, because it seems kind of stupid to have every engine have to call that on their own. It was a kind of an early historical thing, and I think Monty generally nowadays realizes that it was probably a bad idea. So we'll pull that out of there. The other thing you'll notice is timestamps. Timestamps are actually implemented inside the engine themselves. So for instance, if you have a Unison engine that has to do timestamps across, some kind of a clock or a central clock, you're responsible for the updation of the timestamps. So clustering engines can do components like that. So that's part of the reason why you have access to the data at that point. The next thing you can do is just however you insert it. In the case of Tina actually does what's called an encode quote, where it takes the row itself and then encodes the row. Now, the piece that's being passed around there is a piece called buffer. And buffer is the raw byte pointer to the actual data set itself. So we call that's called in memory called unireg. MySQL's original name as a database is unireg. And that format in memory is what we call the unireg format. There is probably only one good reason, and that has to do with one optimization you ever should touch the unireg format directly. The unireg format is actually encapsulated around what's called field methods, and I have slides showing off how to use those. Don't try to take apart the buffer itself. There lies dragons. It's passed in for a few optimization reasons, but for the most part, we should just not touch the buffer. It is a common error I find when I'm studying people's code, that they get it in their head that they can actually beat the encapsulation system because the buffer is not thoroughly privatized, and they'll try to decipher the unireg format themselves. That is a really bad idea. It is passed in so that you can shoot your own foot, and that is the only reason why it is passed in. So just on a note, probably you shouldn't be touching the unireg format. So buff, the thing you see up there, you probably don't need to be touching it. And then stats plus records. There's a stats object with every handler, which just says how many rows you currently have. So that's a per handler thing. Yeah, it's actually used, so Mark's raised his eyebrow there. You can either regenerate it in the info call, which I'll talk about in a few slides, or you can just keep it updated. Tina keeps a constant update during select to know how many rows are in it, so it keeps a constant knowledge of its actual horizon. Is there any questions on this slide? Yes.
SSD is global somewhere?
Yes, that's in a global. That is a HA statistics increment is a global. So this really needs to be pulled out and moved to the upper layer. We just haven't done it yet. Yes.
So where is the actual role? Where is the data?
The actual data I'm going to show, I think, in the next slide. So, but where the data is unencapsulated is actually that buff pointer. So that byte is actually the raw data itself. But I'm going to show you in the next slide how to do it a little more cleanly than touch it. Where is it actually written? The encode quote method is what's going to actually write out the row itself. So Tina uses encode quote, where what it does is it walks through the encapsulated row and then turns it into CSV output. And I think that's the slide I put next. Hope so? No, it's not. Ooh. Okay, I hope that slide's later on. If not, I'll be pulling up source code. Just the thread, I reserve the right to pull up actual source code to show you guys stuff. Yes. So I'm going to move to read, and if I don't have a field, I'll check the slides later on, and I'll pull one of the slides here in the break. Read scan. This is how a scan occurs in the database. So there are two types of read that are going to occur in the database. The first kind of read scan is going to be a basic, we didn't have an index, let's go on and scan the whole table. The section is an index. Almost everything dealing with performance is balancing that equation of what do we use now? Should we scan the table or should we read the table off of an index? Because an index isn't always the fastest way to actually read a table. So that's something to think about. So this is the scan method for reading an actual scan method. So this is where somebody typed select star from foo, and this is how foo gets operated on when it scans the entire table. Now, the first thing it does is it calls something called info. The info, which is broken out in a further slide, is the first touch point for what we call the optimizer. The storage engine handler feeds information back to the optimizer so that it actually can say whether or not a scan should be done at the moment or whether or not an index should be done. And the info call is the very first call to that. Now the info call has optimizations in it. If you say an info, for instance, that it's 0 rows, it just returns and never bothers even talking to the handler any further. It's got a few other pieces, so that's the first touch point into the optimizer. R&D init is the first part of a scan read. What it means is random init, and next is random next. Random init will be called exactly once. Random next is then called every time until the storage engine says, I don't have any more rows. So it just sits there and says, please give me a row, 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 until you return an error message called error into file. Once you call that, you stop actually returning rows. What you would see here is an example of, we go in, we initialize, we read next, and we read next. Looks like this probably had 3 rows in it, and the 4th row, assuming was probably the one that called in. There is also, by the way, though they're not in the slides, there's an RND-in method as well. So if you need to do some kind of cleanup of a scan, you can call RND-in. You don't have to implement RND-in though. This is the actual info call itself. This is what I was referring to as the touch point. And hopefully, even on a large screen, that is readable. Like, I think I've chopped this apart. The info call is the first piece of communicating with the table to know exactly what the contents of the table is. It also has a dual function of being used so that if somebody says show table status, this is where show table status gets its information as well. Now, in this call right here, we see info call, and first thing we do, this being archive, is we say what's the current number of rows available for the table. Archive is what we call a multi-version concurrency engine. It is an MVCC design. In fact, a number of the engines nowadays are MVCC designs. That means that there is a horizon. If you read them multiple times within the same time period, they're all going to return the same value. Now, in the case of archive, what it means is since it's only and it's not a transactional engine, that means when you start reading it from it, whatever rows were there at the beginning of the read are the only rows you're going to see. So if you start 5 readers up and there's a bulk insertion occurring, you won't see the bulk insertion at the beginning part of the horizon. So you never see those rows until that row says complete. Once the bulk insertion is completed, then you would see those rows. So any engine today that can keep this kind of a stable view into a table is an MVCC design, which is pretty common right now among most of the storage engines that are being implemented. Now, in this case, archive says it's deleted no rows because it doesn't delete rows. The if statement you see there is if HA status time, which means that a status time is required, which was probably a show table full status was called, where then it generates things like what was its mean record length, what was its data file length, the create time, the uptime, the max data length. Then we see deletion length, index file length. All of these are used in the calculation of whether or not we should be using the index or doing a scan read. Like I said, if the stats.record you see there that is equal to, so there's only 2 rows, no matter what, we're only going to do a scan read. Because for 2 rows, we're going to do a scan read. There's a way to force that. That's what we call lying to the optimizer, which is done on a number of the engines, to actually force the optimizer to do what they want. For the most part, you shouldn't actually have to lie to the optimizer. You can adjust the cost equations to the point where you never need to lie to the optimizer. But frankly, sometimes it's just easier to lie to the optimizer. For instance, the memcache engine for rows always says it has some god-awfully large number of rows, so that no matter what, it always uses indexes. That's kind of the case, because it just always wants to force index creation, because scan cost in memcache is, well, no rows return, because it has no ability to scan. So it always forces index usage. So in this case, you can also see HA status auto. If somebody needs to know the actual current auto increment state, that's what's called during that period. In the case of archive, it flushes out the table to make sure that the correct stats information is actually stored. So that info call would determine what the next call would be. Now, this is the random init. How are we doing for time right now? Oh, we're doing fine for time. Next month, too fine. The random init is what we're going to use to actually start up the read. So this is a notice that, hey, we're going to start doing a random read. You'll notice that it has one value passed to it, which is a Boolean called scan. If scan is true, that means that it will actually scan forward. That means you're going to be told, by the way, the scanning that's about to happen is always going to be forward. I'm not going to ask for a row twice. We're just going to be scanning forward. And when I talk about random next, random position y that is Boolean isn't always true. So this means that, hey, we're going to be reading forward. Yes? It can potentially be read twice. Order by operation. If the order by operation, if you do a full scan on the table, so let's start doing a scan. So to do an order by operation that required a full scan of the table, so we scan the entire table. Based on flags you get, your R&D init may be called again and being told, by the way, I'm now going to read you randomly. And there's based on a thing called position, which will allow you to reposition yourself on rows. And I'll show a position call here in a minute. And I'll talk a little bit about how the order by operation is actually implemented. So for the most part, scan is always going to be true, except in the case of an order by operation. And I'll show you how they implement that. Any other questions about R&D init? Just to give you another example, if you were inside of, this is the InnoDB example. InnoDB actually just starts a scan up on its primary key index. A lot of engines will actually just find out their key index and read. The AWS engine, for example, is an engine where it gets all of its keys, it keeps an ordered list of its current key list, and then just walks through its ordered key list at that point. So that's a little bit about how that's actually implemented. So this is the point where if you've got a need to initialize some kind of index, this is how you go about doing it. Yeah, it always reads off. It uses its index to actually implement scan. This is the R&D next, and this once again shows the implementation via the InnoDB storage engine. R&D next, all it says is give me a new row. You'll see once again that it passes in that buff. I had better have a slide, if not I'll be adding one in the middle part to discuss what that actually is. But that buff, like I said, is kind of a buyer beware. I wouldn't actually suggest using it. I'm going to show field object methods and how to use field objects. But that's where the data will be initially stored. So R&D next will be called again and again and again and again until you say that it's over. And the return key for it is HA error into file. As soon as you return HA error into file, we stop calling R&D next and we stop trying to retrieve records from the engine. But it's the engine's responsibility, the table's responsibility to feed rows back. Now, let's take this and extend our information a little bit. Let's talk about how an update actually works in MySQL. Was there any questions on the R&D next? Pretty straightforward? Okay. The update row is implemented by, you have to do a pre-read to implement a update, same thing for delete. So this is the case of Tina operating. This is once again a scan read. So as you can see, we do an HA info call. What then we do is we init, so that's the fact that we're going to start a scan read. Then what we do is we do call, and then Tina implements something called extra. You didn't see that with archive. You'll notice that there are default methods that you don't have to implement. If you don't implement them all, everything works just fine. Extra is a set of hints to tell the engine about what's actually happening around it at this time. There are something like 36 hints that can be given to the storage engine. InnoDB, I think, implements 6 hints. MySQL implements almost all, and almost no storage engine other than those two implement any hints. They're not frequently used. But so you can safely ignore extra calls and there's no big deal. No penalty. So in this case right here, you can see extra, and then Tina starts reading a row. So it reads a row, reads a row, reads a row, reads a row, and then on the upper layer, we actually do a match on the predicates from the where clause. And we say, this was a row that we actually need to alter. So what then is called is update row is called at that exact point. Update row, you'll pass in 2 components, and I'll show you that in 1 second. The R&D next is called, the next row matched, and then R&D next is called. Notice that R&D next call is followed by extra, which means that HA error in the file was actually called. You can see Tina implements R&D in, and it actually has a meta file right out, and then it calls R&D in it closes out its R&D call. So this is a scan read. This is important also, because when I get into indexes, realize that indexes work the same way. The index call is made, and immediately after an index call is made, if it matches, update row is called. So you would do you would sit there, it would do a read on an index key or on a scan, and then it calls update. So you can always reliably know that update was called right after the last row it matched. A number of the engines keep a context of the last key read for this reason. Not all engines, but some do. This is the code to an actual update row itself. Yes?
So, if you update the key value, do you send it as a insert or is it?
It's the engine's issue. I have thought about adding a call such that somebody could say, I don't implement update, just please call delete and insert instead for me. But I haven't done it. But that is a possibility to do something like that. But today, an update has to handle that. So if you have a conflict on your key, so what happens if you have a primary key and the update occurs on the primary key? You're responsible for deleting that row from your actual handler and then reinserting the new row. So there is no magic that exists for handling an update on a conflict. An update on a primary key conflict, you've got to implement it yourself. If we were looking at, for instance, if we were looking at, say, the memcache engine for this right here, the memcache engine, actually no, the memcache engine just blows everything away. The HTTP engine, though, for example, actually does a deletion ahead of time. It determines whether or not the key existed. Same thing with AWS, same thing for NOEB. That's a little bit about how it works. So you do a key comparison. This update row that's here is the update row out of TINA. So as you can see, TINA, once again, the non-encapsulated old data and new data are passed in. Yes?
So, similar question is, how do you extend these to the result? What about things like triggers, etc.? Do you expect when the update was overall, the engine to handle all of it? Or would MySQL call me again and say,
MySQL handles the entire update, the update trigger. So the trigger, if it's a before trigger, it'll modify the data for you. If it's an after trigger, then you never see it anyway. But it's all handled above you, so you don't actually have to deal with it at all. So triggers are, the interface is designed such that triggers, things like stored procedures, you'd have to know nothing about. There are people who write engines that know almost no SQL. It's really not needed. Kind of a weird situation, but it happens. In this case, you can see how the timestamp field was updated, the statistics increment. It calls the encode quote. You'll also note it calls chain append. The chain append is just a method for, the way that TINA does an update on an update row is it appends the new row to the end of the file and then marks the previous row to be deleted. So in the end, it does a resolve at the end of the update and then resolves the deleted rows and removes deleted rows. So it's a late updater for update. I think that's now Paul's engine is a little, well, Paul's engine is a generational engine, a PDXP engine. So it leaves the old row in place and keeps the old generation around. Stuff that's usually in BCC has to keep old generations around until it's okay to actually clean out the generation. So this is the delete row operation. Delete row, similar in context. In the delete row, you see an info call. So the info call itself is actually made. The same thing we saw before. If they would have returned a value of 2 here, it automatically would have created a scan. After that, the RND init call, so the scan read is begun. After that, you see the extra call, and then you read next until the delete row. The delete row is just like the update. As soon as a matching row is found by the MySQL server, it is handled. So you, during a deletion or an update, I guess this is a question nobody asked, but I should answer. You yourself don't have to worry about matching the row. The upper end of the engine actually finds that for you. So you don't have to worry about deciphering the where clause or deciphering the predicates to make matches. That entire bitmap that's created to do that above you is done. You never have to worry about it. There's a way to get access to that information, which is, you can look at the federated engine and it will show examples of that. The federated engine uses this then to send deletions across the wire. So it's an engine that knows how to handle this a little bit better, but that's the basics of how it works. Yes?
So, any thoughts in the future to pass predicates from into the storage API to do things in the storage machine? Presume it's much more efficient.
Oh, yeah. I mean, if you look at the federated example, or even the NDB example, where it's the network database, and the whole predicate key should be sent across. The whole delete key should just be built and sent. Now, can that be done today? The answer is it turns out, yes. There's a thing called pushdown conditions, which I think I have an example for in the ends of slides that talk about that. But in the server, we have a concept of anytime we take a condition, which is a predicate, A is equal to 3, that's called a pushdown. So if we pass that down and the engine says, I'll handle that, we call that a pushdown condition. Today there is only 2 engines that actually support pushdown conditions, which is the NDB engine cluster, and Federated has some limited support for predicate pushdown. When you can do predicate pushdown, they can take whole operations and send them down the engine. The reason why this comes to play is if somebody has a very advanced engine, let's say, for example, they have their own optimizer, they may be able to take that road data, those predicates, send them down, and even though this might be a scan read, they can eliminate rows before the scan read is even started. That is something that some storage engines that are implemented can do. So all that predicate information is provided via the pushdown condition. Yes?
Just a follow-up. So that's value need to be done by the MySQL server, right?
I'm sorry, what?
Who decided to pass it there? Because the MySQL server, not the storage engine. Storage engine is recipient.
The predicate condition of pushing down is done in this way. There is a flag that has to be enabled, which is turned on by default in the database in 5.1. There's a global flag to generate predicate pushdowns. There's a call, just like the extra call. You saw where the extra call was in the stack script, the trace was implemented. There's also a pushdown call as well. If you implement the pushdown call, then you get that information. If you don't implement the pushdown call, you never get that information. So it's basically, if you implement it, you can have access to it. If you don't implement it, you don't get access to it.
One last one.
Oh, no, please keep asking.
Is pushdown the meaning of you pass all predicate to the storage engine or you are selected?
Is it what's pushed down is actually what's called an item object. Inside of the MySQL server, items are the smallest grain kind of object that we have. Items themselves, so you get an item object, so what you then have to do is manipulate the item object. The pushdown conditions are pretty advanced. You can literally it can reverse the entire where predicate for a single table. So let's say that you have a select star from A comma B. It'll actually, and then the where clause is advanced enough to keep for Cartesian from occurring. What the pushdown condition does is it actually takes the A key and then rebuilds the algebraic notation for that based on the item trees. So it actually puts together the and, the ors, all the paren calls, and even the function calls. And then once you look at that information, it's up to you. For instance, a pushdown condition on a function call can even occur if you can match a function name. If you implement part of a function name on a pushdown condition, you can do that. One of the most basic optimizations that no storage engine today implements is the, I think it's the concat function call, where you can actually say, I want, values of 6 to 10 for, the given field object. Well, who cares about that? Well, if it's a blob, you could actually eliminate partially part of your blob read if you can implement that. But today, no storage engine does. So today it's a little more advanced than any engine actually knows how to use. It's only the MySQL cluster engine that really knows how to really start using that interface. And for that reason, I think we started, Patrick Galbraith, he doesn't work for MySQL, he works for a company called Grazer. He works on the Federated engine and the ODBC Federated engine. And he's got examples of pushdown conditions that he started implementing. His are probably easier to understand, so if you want to learn more about how these conditions do, because frankly, he turns predicates into SQL statements. And it's really kind of easy to read SQL statements to understand what exactly happened in the code. So if you want to learn more about pushdown conditions and how to do advanced predicate work, what you want to do is read the Federated engine code, so ha_federated.cc. And I think the call that's most useful is called create_where_key. It's probably the most useful for understanding how to take apart the predicate conditions. Create_where_key. It's kind of sick that I can actually remember that. So, yes?
All these calls, how do you handle blocking?
I'm sorry, what?
The dog is very transparent.
No. Well, I'll talk about that when we get into the field pieces. This is delete row operation, like I said, so you can see the delete. This is actually how the delete call. Once again, we see a buffer, and that buffer is going to be a composite of the data that was passed into it. Once again, I'm going to point out you don't actually need to touch buffer. And during the break here in about 3 minutes, I'm going to make sure I have slides that show you how not to do that, because you really shouldn't do it. This is once again Tina. You can see how Tina just calls its chain append. It deletes one of its stats record. And this is how it's sitting around and implemented. So, the important thing to know here is that delete row is always going to occur right after the key or the scan read. That's really the big thing you got to keep in mind. Because the previous key is important when you're calling delete table. Because if not, you'll end up having to take delete table apart and pull its key apart. Which some engines do. I think Memcache, HTTP, AWS, BDB engine, all actually took those key apart. But technically, you don't have to keep the old key around. So, yeah.
In the past, so people, this point of view, I mean, people do structure, that's structure.
Yeah. I'm not sure can you state that again? I'm not sure I understand you.
Okay, my question is, what information is
In the bus? Let me pull up an example after the break, and I want to show you guys how to do that. So yes. Well, let's say up to the actual engine itself. You have to, by the end of the scan or the end of the index read, you have to have deleted it. But in the case of, for instance, Tina, you can see that the row, until R&D end is called, deletions don't actually occur. But by end of statement, it's expected that the deletion actually occurred. So, on that note, I think I want to make sure that my slides have field pieces in it, and I think we're at the, is this the time for the break right now? So it's 5 minutes to 3. Let me see what the next slide is. Actually, I don't want to get into index reads. That's a long topic to start. Delete. So does anybody have any more questions on delete row? Okay, on that note, I believe we come back in 30 minutes. So thanks very much. So is that on screen? Okay. Now we went off and talked about delete row. Does anybody have any questions coming back on delete row? Okay, if there are none, what we are going to do is I'm going to talk about write row again, but I'm going to show a better example. When I went through the slides, I realized somehow there's about 3 slides that got cut out, and they were kind of important slides. So this is the write row method I'm going to talk about, mainly because it was the one that was actually on my laptop. So write row, this is the Memcache write row. This is a pretty modern one. So write row comes in. Memcache is a storage engine that has a primary key storage. Namely, it requires a primary key to exist in a table for it to actually store anything. It doesn't have any kind of hidden primary key system. It must have a public primary key that was actually implemented in the environment. Now, what you see here is the actual write row call. You can see the debug enter, which talked about before. And then what you can see is actually how it finds the primary key itself. Now, this is a pretty good little example here that you want to kind of observe. What you see what it does is it does table-s primary key. That's the shared table component. It says, find me the offset in the array of key info for the primary key and give me the key part, which is called field. What that does, it returns a field object. Field objects are how we actually pass field information around. They are the kind of the key to actually tracking both any kind of attributes you write out and attributes you need that are parts of keys. So in this case, now field is now going to be the actual key itself. Now, what we then do is we set the org bitmap. So we say that we're going to use all columns. And we do something called a packed row. Now the packed row is how a write row is actually going to be implemented in the case of the Memcache engine. So as you can see, it sits there, comes in, fixes up a buffer that it's going to use. It violates the principle of encapsulation for for the field information. So it does this for a very good reason, but in general you probably shouldn't do it. What it does is it actually takes apart the front row and it looks at what are the null bits. Now, when it loops down, you can see the field, table field, field plus plus. What that is that's all fields that are implemented for that schema. So if you did a create table, A in primary key, B char, C blob, each field as you loop through would be in the order that the table was actually, they'll be in the order that the table was created. So the first, if you go and you did if you called field field name, it would actually print out a string, which would be the field name. If you did a field type, it would actually print out the field type. That's the field object represents the attribute from the actual table arguments. And what you're seeing here is a fairly common method. What we do is we look at the field objects, and then we can loop through the field objects for their current values. They will be set at that moment to whatever the right row is. So the current field is actually set to right row. So each call of that would be each successive call. And what you can see is how this implements it, is it calls pack, which is a command just to strip out leading white characters, and then return a pointer to the actual value of that to where you push it into a field. So what this does is it just walks through field and retrieves the records and stores it into a buffer that we've created. Now, there are similar other methods that you can pull out. You can always pull things like field, val string, val int, and the field object will take its value internally and then return it as whatever you call it. The thing to know about this in particular is this is how MySQL does its auto conversion. So if you ever wondered how a field object goes from being a string to an int, all of that's implemented in the field class itself. So we have a generic set of field objects, we call them, and we get values back out of it. And in this case, in Memcache engine, we actually just pipe it onto a buffer that we create where they're going to send to the network storage engine. Well, Market asked, does it eventually go back to a pointer, or what exactly happens? So do you want to know what's the field object pointing to internally, or do you want to know the answer is that if you want to avoid copying the data, what you can do is you can always ask field for field pointer and for field length. If you do that, it will return the native length and the native pointer to the address in memory that the value is stored at. So you can do that and then manipulate that. This, by the way, is that buff that was passed into right row. The field objects are actually operating on that buffer. So you still have access to the raw row, but frankly, field knows how to actually take that thing apart. And you don't really want to implement your own field types. So, any questions? Yes. Such as? We only pass down to the lower level the actual string itself. If you ask the field for its character set information, you can find out its character set information. In fact, you can see here in the loop, you can see a field is null. Because notice it doesn't even copy it in if field is actually null. So you can ask the field, what kind of, what type are you? Oh, you're a blob. Oh, what was your actual field name? Well, I was field name A. Were you a part of an index? Yes, I was a part of an index. Hey, field, what was your character set that you were implementing? Oh, I was a binary type. Oh, so you were just a blob type. Or, oh, I was a Sweden Latin 7. Oh, you're the default character set. Or, oh, you're UTF-8. All of these pieces are actually passed in via, you can ask for the character set information. So field gives you all the access to what the actual data is itself.
Let's say this is the right path, but giving reading, particularly what the information you want.
I will show you in a second how to do the reading. So any other questions? Okay. Now, let's talk about an index read. Now, we talked earlier about how a read would work if it was a scan read. An index read is different. An index read occurs when the index has decided that, hey, we're going to call this index. We've got a key. So A is equal to 3, and we know that there's an index on A, and so 3 is a value. Now, there's some pieces to this that are above this, but I'm going to back into those in a second. First, I'm just going to talk about the actual index read itself. In the case of index read, what will be called is that He'll be passed that buff, which once again you don't want to touch. He'll also be passed a key length, and an RKey function find flag, which is less than useful. The key and the key length for what I'm going to show you is more of what you actually care about. That key is a raw bit of byte data that represents what the key is. So for instance, if it's a 2-part key, it's going to be the length of the 2-part key. If it's a single-part key, it's going to be the key. That key is not actually directly addressable. If it's an int, it's going to be declared in a network ordered, or in a unireg ordered in-memory for an int. It would take up 4 bytes. If it's a long, it would take up 8 bytes. You can't really directly use the key for the most part. There are some people that directly take the key if their storage engine can just handle an arbitrary key size. But most of the time, I find that you usually want to convert it over to something that's a little more useful. In the case of the index read, I'm going to show you the next slide. It's going to talk a little bit more about this. So this previous guy up here is the find row. So you'll see it's got an internal method that's called find row. And then we go to this guy. Now notice, and I hope this slide is readable at a distance, the things that are being passed in is the buffer, byte key, and the key length. Now, the first thing we do, once again, is find a field that represents the primary key. So we use that by finding the table S primary key component. We look in the key info key parts, and we pulled out the field which actually represents the key field. As soon as we take that key field, skip down a couple of lines, and you can see set key image. If you call set key image, you can pass a key image into a field, and then the field will have a representation of itself internally. Okay, so Brian, what's really the usefulness of this? What the usefulness of this is at that point in the primary key, you now have something that you can actually, it's a printable string, or it's an integer, or it's whatever. So that now makes it actually something a little more flexible to deal with. So in the case of what you see here, we actually then call a method called make key, and the make key just builds the primary key for memcache, which is a large composite key. But we can do that because we now have a field method called key field that you can call print string. You can call a string on, or a val string, or a val string, a val int, or whatever else you would need to do. So that's the whole way of taking a key and getting it into something that's actually useful. Take it out of the unireg format, stick it in a field, and at that point, operate on it as operate on the field object itself. Is there any questions about this?
Take you back to the right. I'm sorry.
Oh.
Maybe breaking your flow a little bit. But what exactly are you persisting over?
Why am I what?
What exactly are you persisting? What are you storing?
In the case of the pack row, what it's doing is it's taking the insert. So it's taking the insert. The insert's stored in memory as a unireg format. And what it's doing is it's taking apart the insert based on its field A, B, and C. Now in the case of the memcache engine, what it does is it actually takes the raw data size out of field and adds it and pins it into a string buffer that then sends that string buffer into the data nodes. Yeah.
So that's the.
Yeah,
that's what you would want as a persist if you wanted to.
Right. Now, for instance, if you looked inside of NODB, what NODB does is NODB has its own write buffer object type. So what it does is it loops through the field types and then records that into that object and saves it. NDB has a giant case statement. In the case of memcache is kind of a stupid storer, which means that it doesn't really know what it's storing and it doesn't care about what it's storing. If we were looking at the CSV engine, for instance, the CSV engine would break that out and print them out all the strings. So if you go and look at its, I think it's real write row method, I think is what's called, you could actually see how it's broken out into a set of CSV strings. If you look at NDB, for instance, the cluster engine, HANDB cluster.cc, it has a case statement because its engine, and Falcon's the same, actually pulls apart each attribute type and then remaps it to its own attribute types. So it has its own attribute types for integers and reals and everything else. So it actually breaks them apart and actually puts them in its own attribute type. And the opposite is what's happening in the index read. We are actually taking it and applying these back. So in the case of find row, for instance, you would see that we call find row and we make a key, we send that key into the MC agent, and then the agent calls an unpack row, where it just sits there and loops through the field objects and loops through that string it created and pushes everything back into field objects. So the field object is the key to actually getting access to anything of the internals. So somewhere in there, you're probably going to have a for loop that looks exactly like mine in there, where you're going to walk through the fields and either you're going to take values out of them or you're going to put values in them. So it's possible to directly operate on the raw buffer. I don't think any engine currently does. It's a good way to shoot yourself in the foot. I only know one engine that actually does it, and it's not good practice. The best practice is always to walk through the best practice for this is to always walk through the actual field objects and retrieve data out of the field objects. I suspect it's probably not a bad one, but I would probably look more at NDB clusters because it's more advanced. NDB cluster implements all field types, so I would look at clusters. Clusters code is fairly simple to read. The file is ha_ndbcluster.cc, but I would suggest reading that. Index next is just like what we saw with read next. All index next does is it's literally a what is the next call in the index. So in this case, for instance, in this guy right here, higher into file because, well, I think this came out of an engine that only implemented hash indexes, so there's no way to walk the index forward at all. In a B tree, you would have started the scan in index read, and then you would just walk your index. So you probably have inside your own storage engine some kind of a cursor type implementation. So you would have started up your cursor inside of index read, and you would have walked through it that way. So, optimizer. Let's talk a little bit about actually how the optimizer works. So at this point, you know how to delete rows, you know how to scan rows, you know how to update rows. You know all the basic select components. But what you don't know how to do is how do you actually get an index to be used, or how do you get an index to use, or how do you get a scan to occur? Because some engines, you always want to scan. Some index engines, they always want to do index. And there's a cost operation that occurs internally that you can adjust through about 4 or 5 calls. So what MySQL does is it asks, calls walking into it. The first call that's called is actually info time. And what info time does is what we saw earlier. It says a basic couple of things. How bad is the fragmentation? What was deleted? How many rows do you actually have in this thing? You only have 5 rows? Okay, I'm going to do a scan. Oh, you have 300,000 rows? Oh, I think I'll look at an index and see what an index looks like. So it's the very kind of base first, is this even worth doing anything at all? The next thing we can do, though, is we can actually compute scan times and read times. Now, this, once again, is the info call we saw earlier. So just to remind you, this is what we saw earlier when we looked at the info call. You can see where it passed in the number of records. If the number of records were anything less than 1, the engine would have actually just bailed out on itself completely at that point. If the records are a very large number, it's going to look at indexes. So this happens before even the cost equation really starts to happen. Scan time. This is an estimation of what is the measure in disk seats for the operation. This is actually looking at the NODB scan time. For the most part, for most engines, scan times and read times are probably well calculated for you, so you can use the default implementation. Where you generally don't want to use the default implementation is if for some reason indexes are particularly, you want to balance more in favor towards indexes, or you want to actually balance a little more towards scans. So based on what you would like to do, you can balance the equations. By default, if you have a normal OLTP engine, the equations are probably just perfect for you. If not by default, then you may want to measure it out a little different. So this is a scan time. For scan time, all you do is you return what is the current cost of doing an actual scan in the database. It's pretty simple. Yes?
So the question I have is, and actually the comment here gives some of it away.
Yeah.
Are all storage engines going to agree to base the costs, assuming that there's no buffer cache, or? what are we to do about the benefit from a buffer cache, either in NODB or elsewhere?
Well, for a file system one, you probably couldn't really track it for the OS one, but for the NODB pool one, that's where you would want to adjust for it. If you can do if for instance, if you knew, for instance, that the entire table is currently listed in the buffer pool, that might be, and you knew that the rows exceeded, if you knew the whole thing was in, say, memory at that moment, you may decide to give it, to balance it towards that. If you knew it was all flushed on a disk, you may not balance. So it's I don't know if I'm answering the question or not, but it's
Is anyone implementing a dynamic model at this time, or is it all static?
There is a dynamic model that is implemented in, who's got a dynamic model for scan costs? Anybody? I know that there's a couple of engines that do, but off the top of my head, I can't remember which ones do. Usually if an engine has a really high, there's only a few engines that usually favor scanning. Archive for obviously is one. But there's only a few that actually do it.
Well, so I had a problem where the custom engine I was using had a completely broken cost model.
Yep.
And we messed up when we did it.
Yeah.
But I'm doing queries between NODB and this custom storage engine.
Yeah.
So, I got a significant gain once I corrected it, and the plans got a lot better.
Yeah.
But the problem I'm more concerned about is that just in general, when I'm doing queries between storage engines, I'd like to think that they had a similar, comparable cost models between storage engines, not just within the storage engine.
Well, in theory, the cost equation, you're returning a cost value which, if you look at the faults, that's kind of where we measure the balance between the two. So anything else you would actually adjust against. But, it is there's at least a few engines out there that just completely lie as to what their values are. They just have hard-coded values which are too balanced one way or the other. And the problem which I assume you got into the point was, you probably ended up with something like a nested loop join, which was the problem, or some other join condition where it favored one engine where it should have favored the other engine instead.
It was kind of lying in both directions.
So both engines were lying?
No. Our one was kind of lying in both overestimating and underestimating the cost depending on how you call it.
Yeah.
Which really messed up the plans.
I can say that the cost equations are pretty well balanced between the internal engines today, but that's just kind of time over effort, and that's us actually looking at it over time. But the rule of thumb for me is when I have a problem with this, I ask Sergey Petruniak because he understands these cost equations far better than I do, and I ask him how to adjust the equation. What I have done in the past is I've tinkered with it a little bit, set up like examples for myself and seen if the right thing occurred, and tried to adjust my own values when I tried to help vendors implement their own engines. But that's about all I can say. So unfortunately, it's if one engine is very well balanced and the other engine is not very well balanced, it's going to mess up everything. And that's a problem, especially when you're dealing with today, for instance. If you're dealing with a nested, if that forces something like a nested loop join, and that forces a nested loop join, say, on a network database, that's a disaster for everybody involved, because the nested loop join is going to do so many lookups during that period. In the case of engines, say like the Amazon engine, Amazon makes a lot of money because it'll do an awful lot of queries it didn't need to do, since it's a pay-per-query model. Anyway, I don't know if that answers your question, but really there's not an even divide today. It's just you look at the other engines, you run a couple of tests to make sure that your cost equation looks smart, and that's how you do it. Because if not, your users will tell you very quickly that it didn't, that your cost equation is off. So, yes?
So is this being sent to the engine for every quarter?
Scan time is called, I think it's called every time. Yeah, it's called for every query, so you can't adjust it every query.
So I'm not clear exactly who is supposed to estimate time, is it the engine or is it MySQL?
The engine. You're supposed to estimate what is the cost time for the retrieval time on a currently scanning engine.
So we have to do that query that is supposed to do that. If it's a range query, we have to evaluate all of
let me show you a little further in that. All it wants to know first is what is the scan cost. So what is the cost to read every row in the table? The second, or the counterpart to this call, is the read time call. And the read time call is where we start looking actually at the index itself. And there's two parts to actually determining which indexes to use. In the read time call, notice that we pass in the argument to what is the actual index. We look at how many ranges are existed, and the estimate number of rows and ranges, which is, let me jump forward one question, which is this call right here. We call records in range, for instance, to find out how many records we think that are in the B tree at any point. So you should be able to get an estimate of the number of records. If it passes in a range of, say, between 2 and 7, you should be able to say, well, I think I got 20 keys there. And you should be able to give an estimate back. So once you give that estimate back, we start using that, factoring that in the cost equation to figure out, okay, so this guy says there's only 12 records in his range, and this guy says there's 200 records in his range. If we're in the 5.2 code base where we're looking at, for instance, a hash join, we know that the smaller side should be on the left-hand side and the bigger side on the right-hand side. So we start adjusting that. Now, once record's in ranges, and record range is really simple. It says, here's the actual index value, here's the minimum key, here's the maximum key. And then it's then passed into read time, where read time is then told, this is what we know so far about you. And we're going to then compare that to the scan time cost. And we're going to compare it based on, we picked out an index and we say, this is the index, it's got this number of ranges implemented in it, and at this point, this is the number of rows we think it'll retrieve. So you then go in, make your calculations on how many rows that you do based on that, and then we compare the scan time and the read time with each other and say which one really looks better. And not only which one looks better, but based on other keys that might be, or other fields, if we can only use a particular index, say on this table, not another index on this table, which one would be the better table to actually scan against? So, there's some black arts in doing this completely. But then, the literature at this point really doesn't have a lot of talk on how to actually federate engines together. So far our work seems to work pretty well. But the thing is that the scan time and the read time costs are really going to be based on the implementer themselves. If the implementer can come up with a good balanced cost between good balanced numbers between the two, we're going to do really well. If not, it's not going to be good. Any questions? Okay. Now, lots of transactions, anyone? This is one of those topics where I'm going to show some slides, and we'll see how many questions get asked. The lots of transaction system is very, very complicated, and I'm going to show you a very basic type of transaction. First thing, we're going to first talk about what store lock is. Store lock is the difference between row, page, table. So, if you've ever wondered how an engine actually says, this is what kind of lock we are, this is how it says it. So, by default, MySQL is a table locking engine. That means by default, if you use one of the default implementations, you're going to get a table level lock. Now, after that though, you start modifying it, you can actually decide what kind of locks you actually have. Do you actually need table level locks on updates, but you're good for concurrent insert? Do you have a need for do you not need any locks whatsoever? Can you handle, all this stuff gets played out inside of the store lock code. What you're seeing right there is the default store lock code. If you looked in MyISAM, you'd be seeing the same. Both Tina and MyISAM are both table level lockers. So those, 4 or 5 lines of code right there are all that needs to be done for a table level locking engine. Now, if we get into something that's a little more different, this is Archive. Archive is actually, and I'm not even sure I showed off the full, yeah, I do show off the full, is actually a more advanced locking engine. Because, for instance, it can actually handle even more types of locks called write delay locks. Now, in it, you see from the if lock, TL ignore, lock type TL unlock, write concurrent inserts, TL write. What you're seeing right there is the code that actually degrades all of the write locks into read locks. So it actually downgrades all write locks into read locks because it tests concurrent inserts. So it says, I know you said you came in that you really needed a write lock. but I don't need you to put a write lock on me, so I'm just going to downgrade it to a read lock. You can also downgrade other kinds of locks. There's what's called the delayed lock. The delayed lock is, if anybody's ever seen insert delayed, insert delayed is implemented in MySQL by keeping a big buffer and then flushing the buffer every so often, locking. Archive does it a little differently. What Archive does is it says, you know, I don't actually have to, I can interlace incoming rows all the time, and I don't need to worry about, you know, setting my horizons. So guess what? I'll just take them. So it actually even downgrades a delayed lock and allows the delayed lock to be downgraded into a read lock. And so there is no buffer that's built up that's flushed to the table. It just handles it all concurrently, but it's able to use it to optimize to know that it doesn't actually have to tell an incoming select that the row actually existed. So it basically, it makes the selects faster. So if you can do an insert delay on an archive, you'll only see rows as they happen to actually manifest themselves. So it's a little different. It's also the only engine that can do that. All the other engines generally are a copy of, today when we look at engines, there's two codes that's either copied. Either people copy the code out of MySQL because they need a table level lock, or they copy the code out of IdentityD because they needed a row level lock. That's pretty much generically all the code we see. In fact, I don't think I have seen anyone write anything unique in this code base. It's usually one or the other. Which probably means it also be factored down to a single flag that says if I do rows or if I do whatever. But this is what it looks like. I don't know. Has anybody here actually ever had to rewrite a store lock implementation? Did you have to do one?
Yeah, they did. Nitro does it.
Oh, Nitro does it differently? What do they have to do? Or is it?
They're locking as a little lower level.
Oh, they don't table lock? Yeah, there used to be code in the BDD engine when it was still in the tree that actually showed page level locking and how to implement a page level locker, but there is no currently page level locking storage engine, so there's no examples. You have to go back and look at it in an old version of MySQL. Store lock code hasn't changed in years. Now, external lock is historical, and it's got a really horrible name. Before MySQL had transactional engines, it had the ability to have MyISAM lock use an F-lock. In fact, it can still do this. It would call F-lock on disk and F-lock its table so that multiple versions of MySQL could talk to that single bit of data partition over a network drive. Often, which was NFS, which would corrupt, and it was just a bad idea. It's probably going to go away, even for MyISAM to do that in the near future. So that external lock code was where that lock occurred. When transactions came along, it was actually overridden to actually implement transactions as well. Yuck. So therefore, what's called external lock, what it really is it started in transaction, is what it means to almost all engines nowadays. What you're seeing up there is actually the federated code, which is probably the easier lock code to actually understand. So let me walk you through this entire code base. Now, first thing, you'll notice it's passing in a thing called THD. THD is the current thread context. So it's the current connection context that exists. So that has a place in it, which is called the slot, where you can keep information about any kind of ongoing transaction. Now know this. And THD is never shared during a transaction across multiple transactions. So the slot is entirely a safe void pointer to actually use to keep transactional information. Now, what you see here is you see Federated pulls out a thing called TRX, and the TRX is a handler. Notice it's an HA federated handler. So what we do is we've stored a handler actually in the thread context. I'll explain how this works as we walk through the slides. Now, the first thing we come and do, and we ask ourselves, is this an unlock call? If it's an unlock call, that means that transactions are about ready to end. Commit and a rollback is not handled in external lock. So don't even worry about it, it's not there. What it is called, though, is if it's not an unlock call, that means we've started up something. Now, if you look at THD options, and the option is not auto commit and option begin, that means that auto commit has occurred, and we actually just register the transaction as being false. So all we're saying is this wasn't a transaction, keep going in this case. Else, we're not running an auto commit mode, we're inside of a transaction. Now, Federated keeps handlers around because handlers are what you generally have. You have a cursor that you created something on. A handler is a cursor. And you probably have kept your I think every transactional engine we have today that's been implemented has something, usually implements transactions on the cursor. So in the case of what Federated does is it has a handler where it knows that it has an ongoing connection that it needs to keep track of. What Federated does in this case is it looks at it, and if no transaction has been started yet, it actually stores its current handler self inside of the HT slot. So it says, I'll just store myself in the slot and I become the first member of the transaction. If it doesn't, and it sees that HT slot already has value in it, what it does is it looks at an array. The Federated handler has a linked list pointer into it where it can look at the next handler. So one handler, once it's inserted, it looks in the array of the handler and attaches itself to the next handler. So it has multiple, so every new handler that comes in, it stores itself in a linked list. Because what it does later on during a commit or a rollback is it calls that cursor back up and calls commit to each of the cursors in order. Follow me? So this is probably the easiest example of how an actual transaction is implemented. The NODP code is actually not much more complicated than this. And the cluster code is not much more complicated. The only thing that you don't see implemented here is Federated tables don't implement what's called lock tables. So there is no lock table implementation. So that's the key piece that's missing. The other piece that's missing is, usually is in the external lock code is when you decide what the isolation level is. So there's a variable in THD that will tell you what the isolation level is. So it will tell you the behavior that you should be behaving at for the next call. So if you're following me here, external lock is also where you need to figure out what your isolation level is. Yes?
What determines which one is not external lock versus external lock?
Trying to make sure, I think I got the slide. I thought I had it. If I'm remembering correctly, external lock is called and then store lock is called. So I was going to look to see if I had a double notice of that, but I'm pretty sure if external lock, and Brian shaking said yes. He deals with this stuff pretty much every day as well. So Brian is one of the guys here in the front office, by the way, in the front. And it's great. He works also in storage engines at MySQL. And it's confusing that there are two Brians. Yeah, I agree, Brian. So the external lock, anyway, but you can see how it keeps track of its cursors. I think NODB keeps actually a similar list array of all the cursors that have been called. In most cases, it's something like that that's done. So that's actually how it is. But you have that slot, so whatever you would need to say to eventually call the transaction, you keep it in that THD slot. Because that's what's going to be done. That's what you're going to get when you call commit. And the next thing we're going to look at is how the rest of the commit. Now remember, back in, yes? The THD is only visible within the current thread context. So you don't have to worry about it somehow getting mixed in with another thread or another transaction context.
You said it's locked in this for that particular.
Yeah. Any sub-transactions you'll see as sub-transactions.
But can the parent transaction get information on the sub-transaction?
Yes. You've got the slot, so you can store anything in it. So if you support sub-transactions, you're going to be storing some kind of structure in the slot. And really all the slot is a void pointer. That's all. In my opinion, actually, the slot should be passed in as a void pointer into the external lock code. You shouldn't have to extract it out of the THD. I consider that kind of fishy. But that's the way it's implemented today. So let's actually, now notice this. This is something we saw very, 2 hours ago. This is the handler tenant itself. And this is where we declared that actually a transaction, by declaring that you have a method called commit, that means we declare that you actually have the ability to handle transactions. Here is federated commit. So this is actually how commit is done in federated itself. Notice that this is a handlerton call. It's not called on any particular cursor, not any particular handler. It's actually called to the storage engine itself. It says, here you go. Here's the THD that a transaction occurred on. You need to commit whatever you've been storing here. That is passed in, and as you can see, if all, this is the case of sub-transactions versus transactions, which Federated only has full transactions. You can see what Federated does. Federated pulls that TRX back out, and then it walks that linked list that it has and calls commit on each of the individual handlers. By the way, this is a commit that's not using XIDs. So this is a simple non-XA transaction. An XA transaction call looks almost the same, except the difference is it also would have passed in the XID. So you would know what the XID is for XA.
And there would be a similar way to how Federated commit was set up inside of the XA.
I'm sorry, what?
So like in the slide before, you showed that the commit is Federated commit.
Yeah.
But you said equivalent is a structure for XA.
Yeah. So they're pretty much the same calls, but with the word underscore XA after that. Yes?
What about the unlock? We have store lock and
External lock, if you implemented the netlock system like my ISIM originally had, if you saw at the top of the if condition where the external lock calls, I said, if not this, if that had been passed in, that's where you would do a unlock. But I'm assuming nobody is going to implement an F-lock engine anymore. Had its uses, corrupted a lot on NFS, but not so good. I think I spent more time apologizing for it as a feature, not actually seeing it being rewarded for it. This is the federated commit call. Like you can see what I said, walks through the handlers, moves through the handlers, calls commit on each of them. In the case of it, it's actually keeping connections open to the remote store, the remote ends during this, and then calling commit on each of those. This is a rollback, same thing. HTON THD passed in, whether or not you should roll back everything. And you can see it just walks through the handlers, and it would be sending a message to each of them. Notice it clears the slot at the end because it says the transaction is over. You're responsible for clearing that slot, not the, there's nothing else that will do that cleaning for you. Is there any question? Rollback's pretty much the same thing as commit, just you got to do a rollback. Any questions on it? Yes. Yes.
Any support for save points?
Yes. I don't have any slides in it, but I will put up a look and show you how save points run. But that's part of the reason why I have if all in there is to actually avoid the save points. But yeah. So there's full support for nested save points and all that actually. So I think InnoDB is the only engine that implements them right now. I don't actually know if Falcon does. Actually, Solid does. I know Solid does an implementation of it too. Solid code's pretty easy to follow too if you're looking at another engine. Well, other questions? Okay, let's go to the next one. So we've now gotten through transactions, and we've talked about really simple transactions. But is there any more interesting handlers and calls? There are something like about 19 handlers and calls today that exist. So there's actually a lot of advanced stuff sitting in Hamilton that can be done. A lot of it was on cluster, some of it for other storage engines. So when you look into the how am I going to differentiate my engine, some of the questions sometimes, and these are two examples, the discover call and the find files. The discover call is for file discovery. So storage engines that implement file discovery, which there are 3 in existence today. This is archives discover. It's a little easier to understand than some of the others. Archive actually tracks inside of its own meta information, the information on the original creation of its own table. What it can then do is provide that to the upper end and say, hey, I actually exist as a table, so why is this useful? LiveJournal copies around ARZ files, so they generate log files out of archive and then move those files around in their environment. When they move those files around, they can copy them to another MySQL server, and as soon as they're copied into a data directory, they're immediately discovered as soon as somebody does a select call. You do a select, they're immediately discovered. You do an insert, update, they're immediately, an update, throw an error. Insert was immediately discovered. In the case of, say, NDB cluster, if you've got 3 front-end MySQL servers and you create a table here, it's automatically discovered by any of the other front-end servers that have access to that same storage node environment. The same thing with Memcache. If you've got 4 or 5 MySQL servers talking to a Memcache environment, as soon as the table is created on one Memcache node, it is immediately discovered by all the other Memcache nodes. So that's how it works. I just figured out a feature. Find files is implementation, another specific. It implements the files information schema. So if you want to provide that information on your actual data set files to the users, this is how you do it, is find files. There's actually components in there for like hijacking replication. So if you've ever been interested in how to write your own funky replication system, it's actually all sitting inside of the Hamilton calls. Just on a key note to know about. All of this code now sits in there. So there's quite a bit that you can do if you look for the Hamilton. At some point I'm going to write I had an example which unfortunately got lost when my laptop got destroyed, which was the multi-master replication with the storage engine handling the mastering of machines back and forth. That can all be done from the storage engine layer. So you can do an awful lot looking at the Hamilton. But it's a very long list of methods. Any questions on that? Yes?
If you're talking about custom replications and not going through the bin log in this example?
Well, that's the interesting thing, is you can do custom replications with it, and you can also both send messages to the bin log. Let's say, for instance, that you've got extra data coming in from other nodes. You can actually pipe data to the bin log and pipe it into the replication. There's a really smart Ukrainian that actually wrote a file system replication system where he kept, I can't remember how this works, but somehow he discovered files constantly as they were being inserted into a file system, and then injected them into MySQL, which then handled replicating copies of those files throughout their network. Pretty neat little engine that did that. So that's one thing you can do. So you can insert or inject components into the replication stream. The other thing you can do is you can put a listener on the replication stream and listen for all the replication messages. So you can literally listen as the bin log listens and find out everything that's going on throughout the database. The listener one I've not seen anybody exploit yet, but there's obviously 2 or 3 products that could be written around just exploiting listening for the replication stream. Auditing, all kinds of stuff. Yeah. The answer is not yet. Can't do that just yet. The closest to that is you'd have to create your own standalone daemon that could just speak enough of the protocol. But if you see Lars walking around here, say, hey, Brian keeps talking about, or told me to ask about replacing the bin log with a storage engine. And I go, yes, he did. And then offer him beer. So the answer is that it'd be great if I actually got Lars drunk based on these jokes. Anyway, so if anybody wants to, he's a really great guy. I'm sure he's well worth getting drunk. So the thing is that Lars knows about that, and it's in the eventual design to change it to do that. So there's still some pieces, but there's enough pieces there to make it mostly happen. Because if you caught all the messages from a storage engine and then just set up a simple pipe across the network to any other listener MySQL servers, you could actually create it's possible to create a synchronous replication inside MySQL through this implementation. So by putting a listener in, you could create a synchronous replication that then inserted statements across all of their nodes. So it is possible to do this. Nobody's done it yet. It's probably worth the money. The last little piece I'm going to talk about before I get into the final pieces is the information schema. And the information schema is another plugin type that goes hand in hand with the storage engines. So at some point you're going to say, I need to expose data to my users. I need to know lock information. Anybody who's ever had to look at the show InnoDB status is probably going to walk up to Heikki after this talk and say, why haven't you implemented an information schema yet? There's a great, probably the most advanced set of information schemas is Jim Starkey's right now that came out of Falcon, which had the involvement of me saying, Jim, you need to implement this, Jim, you need to implement this, and Jim saying, no, not today, not today. And then finally getting an hour, looks at it, and then sends me a piece of message saying, this is cake. So everything you see when you look at the Falcon demos and they show all the information schemas, which all look pretty and users love this stuff, he did that in 3 or 4 hours. The information schemas are very, very easy to extend. There's public examples in Falcon, there's public examples inside Memcache. The Memcache engine also has an information schema that uses it to monitor all local memcache engines. Somewhere around here is Jan Neske, who keeps thinking he's going to take one of the libraries, what is it, Doug's library for Cigar, which knows all the operating specifics so that you could like look at a table inside MySQL and know all the ongoing information about the operating system, so you can select it like a database. But for people who are writing databases, this is your way of providing information about locked usage, information about current internals. It's a real differentiator because frankly not enough storage engines do this in MySQL today, and users really, really want to know what exactly is happening inside of the engine. What are my lock conditions? What are, how much memory am I actually using? What's the last state here and there? So I'm going to show you how to implement these. They're really simple. So first thing, what is an information schema? If you use the information schema, you'll see, I think 16 built-in information schemas today. If you do show tables, you'll see it. These are materialized tables, so there is no actual FRM. They're not in a data dictionary. They're tables that we generate on the fly based on need. Now, they too have a plug-in interface, so they're their own plug-in interface. So this right here is shows off the plug-in information for a memcache, for the memcache server information schema. You'll notice different from the first slide you saw that the MySQL information schema plugin, which is the declared plugin type. You'll see it in a memcache server IS and memcache servers. Memcache servers will be the name of the table if you did a show tables inside of the information schema. Memcache init calls the init. Memcache dinit calls for the init. This is the IS init. So this is actually how memcache server is actually doing its init. So it calls, it's passed in a structure. That structure is a filler, just like you saw with the Hamilton. But instead of being a Hamilton, it's an information schema. So what you'll see is, notice the key is passed in. We then get the plugin. We take that information, and then we fill in our schema information. So schema fields info and schema file table. The only thing you have to implement is those two's callback. There's a few other callbacks if you're going to implement show commands, but frankly, it's really kind of, I wouldn't personally recommend it. I would just implement just the information schema itself nowadays. The memcache server field is pretty simple, and this is just the DNN, which does nothing. The field info is what the actual table is going to look like. So when somebody goes and then does a describe table or does a select on it, you pre-declare all the field information. This is how all the information is declared inside of this structure. So the structure is a simple pointer to a structure. Name, count, current items, total items, bytes, current connections, total connections, connection structures, gets, sets, hits, misses, bytes read, limits, max bytes, and then a null pointer at the very end. So this information schema, this is what's going to be. So if somebody types, like I said, describe table, these are all the field information pieces they're going to get. It's really straightforward. This is how what's going to be called when somebody actually does a select on the table. If someone does a select on the table, this is how the information is going to be filled out. And this is a kind of a shrunk version of it. But the things that you need to look at, we passed in THD, table list, and condition. That's actually the push down condition. So if you wanted to push down conditions to yourself, you could take that condition apart. So tables, it's only a single table. So tables is just a table list. So we take the single table. We then open up our structure that we're going to supply data on it. And we call table field store. So what we're saying is in field 0, store this data. In field 1, store this data. In field 2, this data. Field 3, field 4, field 5. And all the data will actually be then stored in the actual field. Yes? Yes.
Could you repeat the question?
What he asked was, if this was a really expensive is there any way to narrow down what the data result set that's going to be sent back? That's actually what condition is. The condition you see is the pushdown condition, or the pushdown condition object. So you can take condition and then take it apart and determine from it, oh, somebody only wanted to know this information on this one particular. So, for instance, if I had 100 memcache servers here, or 1,000 memcache servers, I could actually take the condition apart and then loop through and see which servers they asked for. If they only asked for, were servers in, blank, 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 I can actually see that those three existed and then filter my data based on that by looking at the pushdown condition. So you can do that type of let's make sure we don't retrieve too much expensive information.
What if the field is not crossed?
I'm sorry, what?
What if some field, some columns is select box rather than the word box?
Right.
Miss that, right?
Today there is no way to currently get that. Let me think about that. Is there a way to get to that?
Select B from C.
There is a way to get access to that information. There's not an example up here. If you look at the previous slide where I looked at the, let me answer your question in a more general way. I think people will walk away and wonder about this later on. Now, see that thing up there that says my bitmap, old map? It says debug, temp, use all columns, table read set. What that does is that calls that says I want to know all of the read set for the bitmap. So it says I would like to know everything that was read, that was expected to be read. And this is find row, right? And there's a similar set for write row. And using that bit set, you can actually find and decipher from that whether or not it was in the where predicate or whether or not it was
actually in the
select predicate. So for instance, you can find out, well, the blob was only in the select predicate, so I'm first, since blob, maybe you have a storage engine where you first grab data and then you store, and then you grab a blob. You don't want to read a blob if you don't have to read a blob. InnoDB has examples internally of it doing this, where first you look at the read set, and you say, you know what? You're in the read set, but I see you're only actually in the where predicate, so I'm not going to try to fetch the blob just yet. And once you determine that, oh yeah, this is a good row, then you can look and say, was the blob needed? Okay, the blob was needed, so I'll go grab that field piece. So it is possible to do that, and you can do these also in information schema. So it is possible to narrow, not only using the pushdown condition, the entire predicate, push to the entire predicate. It is also possible to see which particular attributes were actually used and only return them. So it is possible to do that. That's, I was going to say, probably the best looking use of that right now is in InnoDB. Because InnoDB looks at blob implementations, and when it looks at blobs, it then extracts out the blobs that are needed or not needed. So. So one of the things I want to get into is, so why is all this pretty simple? Well, when we implemented this as a loadable engine, it became very simple to do this. Because in this case, you can see install plugin, memcache servers, soname, libcache. I mean, that's all it takes to load a new engine actually into the database now. And uninstall can be done the same way. We can compile them directly against the database, and there are examples of doing that. In fact, there's no code changes whatsoever. You just have to put one little file in a directory. And that's the only difference between compiling in and compiling out of the server. Your question?
Yeah, so actually I'm coming from an angle where I have an existing database and I'm trying to put it in the embedded data.
Yeah.
So,
And which company do you work for? Oh, that's good.
So what if it's not a DLF or not a SO? What if it's an actual server?
You're going to have to write a shim file, because the shim file is the only way to... I've seen a couple of examples of people that have created very lightweight. The federated ODBC connector is a good example of that, because it connects to a remote database, but you still have to have no matter what that shim layer. Now that shim layer that exists, if you communicate via a socket or Unix port, it doesn't matter. It's what matters is there's got to be enough in that shim, in that DSO to make that initial connection.
And because the issue is going to be like, let's say, my server crashed.
Yeah.
Okay, but it's not being started.
Yeah.
So how is there something which MySQL and the server can communicate?
Well, I mean, you have, in essence, when somebody calls an open table, you have the ability to look and say, doesn't exist right now, and there's a return error code which says foreign service is not available right now. So you can return the foreign service not available error code right now. So it is possible. Or what? Or you know, I can do some hackery and call system and do something, open it up. Let me move on to the next piece here. How about testing? Like I said earlier in the slides, MySQL test. The other thing to look at is MySQL slap itself. MySQL slap is great for load generation because just when you think the storage engine works, throw 300 users at it concurrently and actually see if it works. It's a great way to test this stuff. You know, I went over a good chunk. In fact, I think it's the longest of a large public class I've ever given on this topic. But usually if I actually give a one-on-one class, it's about a week-long effort to give people. But it's also usually I sit down and make the engine work. And I don't know, Brian probably goes off and spends weeks at a time with people on this stuff. I've seen engines integrated in periods of times of under a week. And I've seen engines go on for years and never get the integration. I think part of that is based on people doing the integration. If they fight the interface, then usually they have a problem. If they work along with the interface, it works out pretty well. So on the side note. Now, what I was planning on doing was opening up an actual engine, and now that you've been talking all this, show what an actual engine looks like from a VI prompt. So that you can say, I now actually understand this from kind of a standpoint of here's actual code. Because all of this has been thrown at you, but now I want to show what it really looks like when it's put together. So as soon as my laptop decides it wants to return, come on, return. Let me go here. If I open up anything embarrassing, sorry. So what we're going to look at right now is Memcache engine. By the way, just to make your lives easier, there's a thing called the skeleton engine that exists out there. The skeleton engine is a framework for just attaching your own engine into it. It implements all the makefile, auto tools, configures, everything else. If you're wondering why, Paul got PBXD, well, he copied the skeleton engine. And since he fixed something, I copied it back into the skeleton engine. The skeleton engine is a great framework to start writing an engine. I think there's at least 2 or 3 people in the room that even have commit access to it, to make changes to it. But we kind of try to keep that running as kind of a community project to make sure that it's easy for people to have an easy time getting into storage engine writing. So this is the Memcache engine itself. This is its directory that you would go in and pull it up. It's got its configure in, it's got everything, in start. Things to know inside it, you went into source. That's all it is. This plug.in file is only useful for one thing. If this engine needs to be compiled into MySQL, you can literally just copy the source directory into the storage directory, the MySQL source tree, type make and or type configure and then make. It'll actually then just build Memcache into MySQL directly. So you can build and test entirely as an engine which sits outside of the tree, which is much easier. And then if you want to, build a binary with it built into the binary easily enough by just copying a directory right over. As long as the plug.in file exists. So what we're going to look at is I'm going to show you the first thing we're going to look at is class definition. So for instance, this is the example of its share. And this is its actual handler. So these are the methods it actually implements. And you can see these from earlier. Open connection, close connection, pack row, unpack row. Here's from the public methods. Notice its table type, which is Memcache, base extensions, which it implements. Notice table flags, HA, require primary key. These are the index flags it implements, where I talked about index flags. The index type, which is the key bit of text we'll display if we ever need to. Maximum supported record links, maximum supported keys, maximum supported key parts, maximum supported key length. Open, close table, you saw earlier. Here's the write row call. And notice this is the init function. Actually, let's stop down here first. This Notice that there is its information schema plugin, and there it's storage engine plugin. You can put multiple plugin definitions in the same .so, so you don't have to. You have to declare a list of these if you need to do it. So in this case, you can see with its IS information schema and the Memcache storage engine itself. Notice P comes in. This is what we saw in the talk. This is the Hamilton. This is where we set up the state. Notice here's the create, here's the discovery. That's its done function where it cleans up memory if the server should shut down. Looking for here's the open call that uses. So where I talked about open earlier in the talk, this is where an actual open table exists. So you can see where it passes in the name, mode, how it uses its buffer. You can see where it tests its connection. You can see where it sets up its global memory piece for this. You can see where it does its it sets its ref length. Close connection. Here's an open connection. Here's its records and range call. Since it's a hash index, what's its records and range always going to be? 1. So it doesn't even have to look. Here's its index read call. You saw this earlier in the slides. Read range first, which is a look ahead read just to see whether or not pieces exist. Yeah. The answer is that, why does it bother calling this records index? The answer is that it should be fixed onto. It doesn't really need to be. So. Well, yeah. The answer is it could optimize that and not actually call it, because it should know that the cost is always 1. This is its update row call, so if anyone was interested in it. Now it's update row. Yes? Oh yeah, for non-unique. Yeah, if your hash implemented non-unique. So if the hash implementation was just non-unique key, then yeah, you could. This right here is the update row call. So if you're curious to see how the update row looks, notice how it has to double test its keys. We talked about this earlier, what happens if a primary key conflict actually occurs. So that an update updated the primary key. In this case, you can see how it actually compares the current key versus the previous key and determines if they are. It deletes the record inside the Memcache cluster and then actually adds the record back. Otherwise, it is called to replace on the actual record itself. Here's the delete row implementation. There was something we didn't talk about, which I'm going to show you an example of here. You can see where the init, so some internal stuff. Where is position? Somebody had asked me about order by operations much earlier. To implement order by operations, you have to implement what's called the position call and the R&D position call. Position calls are always called after index reads, or they're called after R&D next. What a position call says is that last row, give me a key identifier I can use later on in case I ever need to find that row again. And what you see there is a lookup where it uses a text string from the primary key stored in that row piece. So in case it ever had to be found again, it can know that I need that last row I saw. Give me a key to how to find that row.
Brian?
Yes.
Is that required that you do the right thing on that call? Can you signal I don't support that call?
The answer is there is a way to force it, and I don't remember how it's done. But there's a way to tell. It's not done by a table flag. It's done by something else. I know that Anthony originally was going to put a table flag in for that, but it is possible because, for instance, and I was going to ask Brian, do you remember how to do this? This is one of the ones that There's a way to tell. There's a way to force it to say it's too expensive to ever call a random position on me. Just always do it yourself. And I don't. I need to find either Monty or Monty wouldn't actually know it. Need to ask Anthony. Anthony remembers how to do it. There is a way. We've had one or two engines that couldn't handle recalling the same row again. And so always store locally, keep a local store of all the rows. So if you fetch a row, keep a local store, something number of engines need, but I don't remember what it's called. Anthony Curtis will be around later in the meeting. If not, send me some email and I'll look it up again.
Is this only used for the 4.0 style external sort where it would just sort the pointers and then do random I/O to fetch the rows, or is this used in other cases?
This is actually used in a number of cases. It's also used in order by random cases, or something called order by ran. One of the most common cases I run into people who they've implemented an engine and they don't realize that we've extended the SQL to, believe it or not, update table, set something or another, order by random limit. So just randomly change 5 rows. Which you guys laugh, but there are people actually who use it, and that's usually the ones that's usually the one that breaks most engines, because nobody thought anything crazy like that would ever exist. So yes.
So on those codes, when you do a select statement or start interaction, there is a lot of interaction between the engine and MySQL.
Yeah.
So where is how does the engine know to relate something to a particular transaction? Where are the connections you mentioned? I don't see in the research that there is a connection that assigns to a particular transaction.
Well, you know that remember that the external lock call, beginning all of this, you got an external lock call that had a THD. So if you really need to, you can store a copy of the THD throughout until the external lock call is it up. That's one way to do it.
Within every code?
Well, you can create there's 2 ways to do it. There's a good way and there's a bad way. If you absolutely need the THD in all possible cases, so you need to know the context of the thread operation, what you do is in the external lock call, take the THD and store it in a pointer to the given cursor so you always have access to it. That's one way to do it. The bad way to do it is there's a way to start on, if you read the internals mailing list, I explained this about 3 days ago on the internal mailing list, there's a way to open up the include files to get access to more of the server's internals. And via that, you can call a function called current THD, and you can actually get access to the current transaction state. You can do this. There's an email on how to do this, not 3 or 4 days ago on the internals mailing list for me about how to. But I think it's probably better to actually store current THD inside of external lock when you get external lock, and just keep it there for the rest of the state, and then when you exit, throw it away.
But then, even if I pass or back to then get it again, I will be fine.
Yeah. No matter what, you can always get access to it.
And if I have multiple transactions running at the same time, on each one I'll get the
Well, you only actually have access within the cursor. By default, MySQL only gives you access to the current thread context, the current transaction context. If there's a transaction running in your engine on another transaction context, you have to know about that. So you have to track that somehow internally in your own engine. So there's no specific way to actually do it. If you want to talk across the transaction boundaries between multiple engines, that's the engines currently implement that on their own.
What I'm trying to realize is how do I know particular code belongs to a particular transaction? And since I can have multiple transactions running at the same time.
Well, remember that we stored remember if you look at the federated example, how in federated it took a handler and then stored that in the THD. That's how it knew where it was at. So that's how the THD knew how its member related that. So, any other questions? Well, on that note, I thank you. I hope this was useful for you, and enjoy the rest of the conference.